Yes. Our first speaker is Professor Usman from Firat University, Turkey. Professor Usman to start his presentation.
Thank you very much. I think I can start.
Yes, please start.
Yeah, thank you very much. Good morning, good afternoon, and good evening to all distinguished scholars, speakers, and delegates from different locations of the globe. This is a multidisciplinary conference. Also, I would like to introduce my sincere thanks to the conference committee and conference management to provide me a facility to deliver my talk at this important conference. Let me inform you that this is a multidisciplinary conference, and I am sure you agree with me that every scientist is not familiar with every subject of the science. Therefore, at the beginning of my talk, I'll introduce the basic terms and definition related to the Shear-Modulus effect and crystallographic transformation. Then I'll introduce the result of the experimental studies performed to copper-based Shear-Modulus alloys, copper, zinc, aluminum, and copper, aluminum, mangan alloys. As you can see, the title of my presentation is Physical Factors and Lattice Reactions Governing Shape Reversibility in Shear-Modulus alloys. Metals and alloys have different phases at the different condition, and these phases are described in the phase diagram as alloy composition temperature or composition pressure dependent of the alloys. Beta phases of these alloys mainly have BCC-based ordered disordered structures, and these phases are very sensitive to the external condition, and crystal structures turn into other structures by means of crystallographic transformation. Shear-Modulus alloys takes place in the group. Also, lattice vibration, phonons, internal friction, and interatomic potentials plays an important role in the processing of transformation and Shear-Modulus effects. In the Shear-Modulus effect, first transformation is thermal induced Martensitic transformation and occurs in atomic scale in the material on cooling from parent phase raising, and interatomic interaction govern this transition. Crystal structure of beta phase alloys undergo crystallographic transformations on cooling and stressing, and exhibit a peculiar property called Shear-Modulus effect as a result of this transformation. Shear-Modulus is the ability of material to recover a previously defined shape when they are subjected to the variation of the temperatures. These materials can be plastic deformed in low temperature condition and recover the original shape just by thermal means on heating or the reverse transition temperature after removing the strain. These materials cycle between deformed and original shapes on cooling and heating. These alloys exhibit another property called superelasticity, which is performed by mechanical stresses in a constant temperatures. Therefore, these alloys exhibit dual thermoelastic and superelastic characteristic in memory manner. Shear-Modulus alloys are responsive material and exhibit peculiar property called Shear-Modulus effect. This behavior is initiated by cooling and deformation processes and performed thermally on heating. The materials, I mentioned this details. This is the main processes of shape memory effect. As I mentioned, first step is cooling, and on cooling, the shape of material doesn't change, but the crystallographic transformations occur in the atomic level. Second step is the deformation. This is plastic deformation, and material keeps the deformed shape after releasing. At this deformation, strain energy is stored in the material, and on heating, release it by recovering the original shape. And the shape of material cycle between original and deformed shape on heating and cooling, respectively, in the reversible shape memory effect. In the irreversible shape memory effect, the material is recovered the original shape in the first heating and doesn't go back to the deformed shape on cooling. Shape memory effect and superelasticity is result of the crystallographic transformations, thermal and stress-induced Martensitic transformations, and evaluated by the structural change in atomic scale. Shape memory effect is performed thermally in a temperature interval depending on forward austenite martensite and reverse martensite austenite transformations on cooling and heating. Superelasticity is performed in the parent austenite phase region just above the austenite finish temperatures. And in the superelasticity, the material are deformed in the parent phase region and shape recovery is performed instantly and simultaneously upon releasing the applied stress by exhibiting elementary elastic material behavior. This is temperature hysteresis or shape memory always. As I mentioned, on cooling, thermal-induced Martensitic transformations occurs, and transformations start at MS temperatures and completed at MF temperatures. MS is Martensitic start and MF is Martensitic finish temperature, and below the MF temperature, the material is in the complete product Martensitic phase. On heating, reverse austenitic transformation occur on heating and start at AS temperatures and completed at AF temperatures. And over the AF temperatures, materials are in the parent phase region completely. As you can see, MS and AS temperature, these are Martensitic start and austenite start temperatures are not the same in the Martensitic transformations. Martensitic transformations are solid state phase transformations. Forward and reverse transformation temperatures, forward and reverse transformations don't start at the same temperatures. This is equilibrium temperature, and a driving force is necessary for the transformation. This is the Gibbs free energy curves versus temperature for austenite and Martensitic. On cooling, Martensitic transformation occurs and follow this ring. This is equilibrium temperatures, and Martensitic and reverse austenitic transformation doesn't occur at the same temperatures, and a driving force is necessary due to the solid state phase transformation. This is Gibbs free energy, and this is chemical energy. In the chemical reaction, forward and reverse transformations occurs at the equilibrium temperature, but Martensitic transformations doesn't occur at the equilibrium temperature. This is the stress-strain characteristics in Shear-Modulus effect and superelasticity. In the Shear-Modulus effect, the material is deformed in the low temperature condition. This is plastic deformation, and martensitic material keeps the deformed shape after glazing. As you can see, early stage of deformations exhibit elementary elastic material behavior. And stress-induced martensitic transformations occurs at the plateau level. As you can see, in the superelasticity, stressing and releasing paths are different, and hysteresis loss refers to the energy dissipation. This is another stress-strain behavioral shape always at a temperature between martensitic finish and austenitic start temperatures, and stress-strain profile exhibit different characteristics beyond Shear-Modulus effect and superelasticity. This is another illustration of Shear-Modulus effect. In the Shear-Modulus effect, the material is deformed in the low temperature condition. This is plastic deformation, and after releasing, material keeps the deformed shape. On heating, the material records the original shape and cycle between original and deformed shape on heating and cooling. In the superelasticity, the material is stressed in the current phase region and record the original shape after releasing, exhibiting elementary elastic material behavior. This is the schematic of Shear-Modulus cycle in the crystallographic level. Let me inform you that Shear-Modulus effect and superelasticity is performed in the beta phase region of the material, and ordered phase is essential. On cooling, ordered parent phase structures turn into the twin martensitic structures by means of thermal induced martensitic transformation. Second step is the deformation, and with the deformation, twin martensitic structures turn into the twin martensitic structures by means of stress-induced martensitic transformation. On heating, stress-induced structures, twin martensitic structures turn into the ordered parent phase structures by means of reverse austenitic transformation. And crystal structure of material cycle between ordered parent phase structures and twin martensitic structures on heating and cooling. Let me inform you that stress-induced martensitic transformation occurs by means of deformation at the first step of the transformation, but during this cycle, stress in the twin structures is not a result of stressing, but it is result of the thermal induced. This is a schematic of superelasticity in the Shear-Modulus. As I mentioned, in the superelasticity, this material is stressed in the parent phase region, and ordered parent phase structures turn into the twin martensitic structures by means of thermal stress-induced martensitic transformation. Upon releasing, the twin structure turn into the ordered parent phase structure by means of reverse austenitic transformation. This is the three-dimensional illustration of Shear-Modulus mechanism. On cooling, ordered parent phase structure turn into the twin martensitic structures by means of thermal induced martensitic transformation. And with the deformation, twin martensitic structures turn into the twin martensitic structures by means of stress-induced martensitic transformation. And on heating, the twin martensitic structures turn into the ordered parent phase structures by means of reverse austenitic transformation and crystal structure of materials cycle between ordered parent phase structures and native Martensitic structures on heating and cooling. Superelasticity is also linked with stress-induced Martensitic transformation, which is induced by applying mechanical stresses. With this stress, parent arsenic phase structure turn into the complete determinate Martensitic structure, as in the deformation step of Shear-Modulus effect, and determinate Martensitic structure turn into the parent phase structure upon relation. The crystal structures cycle between parent phase structures and determinate Martensitic structures on stressing and releasing. It is important that stress-strain curve exhibit nonlinear behavior, and stressing and releasing paths are different, and hysteresis group refers to the energy dissipation. This is the stressing and releasing diagram in the superelasticity. As you can see, stressing and releasing paths are different, and this slopes refers to the energy dissipation. By the stressing, ordered parent phase structures turn into the determinate Martensitic structures by means of stress-induced Martensitic transformations. Martensitic transformations are first order solid state fast transitions and occur in a fifth step with the cooperative movement of atoms in displacing manner. Therefore, these transitions have diffusionist character, and product Martensitic phase inherits the order of parent austenite phase. Mainly, Martensitic transformations occur into basic step in the beta phase region of the material. These are Bain distortion and lattice invariant share. These are basic beta phase structures in the beta phase region of the material. This is ordinary body-centered cubic structures. This is the cesium chloride type crystal structure. This is DO3 type crystal structures, and last figure represents the L2-1 type crystal structures for the ternary coupled shape memory alloys. Bain distortion is mainly effective in ternary coupled shape memory alloys and consists of an expansion of 26% in 001 type axis called Bain axis, and a completion of 11% in the 110 type directions perpendicular to the Bain axis. There are three Bain axes, and these are 100, 010, 001, and BCC based unit cells turn into the body-centered tetragonal structures as three variants with the three different orientation. This is the body-centered cubic structures with the Bain distortion. Cubic structures turn into the tetragonal structures with three variation. Lattice invariants occur as Martensitic variants on 110 type planes of austenite matrix, which is basal plane of martensite. These shares occur in two opposite directions, 110 type direction on the 110 type planes. The 110 plane family represents 6 certain planes, and totally 24 Martensitic variants occurs. These planes are listed as follows: 110 minus 110, 101 minus 101, 011, 01 minus 1. Lattice invariance and lattice twinning is not uniform in coupled shape alloys, and these shares cause the formation of layer structures. 110 type planes of parent phase turn into the unusual layer structure, which consists of an array of close packet planes with complicated stacking sequences called as 3R, 9R, or 18R martensite, depending on stacking sequences. on the closed bucket planes of the ordered lattice. The periodicity and therefore the unit cell is completed through 18 layers in directions that in case of 18 are Martensitic structures. These are the formation of the layer structures. This is the stacking of one type planes of austenitic matrix. This stacking is AB, 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 AB. With the lattice invariance, this stackings turn into this stackings AB, ABC, BCA, CAB, and A for 18 are Martensitic structures. Also, as you can see, product phase exhibit layered structures. This is another illustration of the formation of layered structures for DO3 type current phase structures. These are the basic terms and definitions related to the Shear-Modulus effect. And experimental studies were performed on two copper-based Shear-Modulus alders. You can see the alders compositions, chemical composition of the alders, and these compositions were selected in the beta phase regime of the material. Also, Martensitic start and Martensitic finish temperatures are over the room temperature. Both of the alder samples and both of the alders are completely in the Martensitic state at the room temperature. Specimens obtained from these alders were solution treated for homogeneations in the beta phase field as following, then quenched in ice brine and aged at the room temperatures. These temperatures were selected in the beta phase regime of the material. These are 830 and 700 degrees for copper, zinc, aluminum, and copper, aluminum, mangan alders, and homogenization time were selected 15 and 20 minutes for copper, zinc, aluminum, and copper, aluminum, mangan alloys sample. Powder specimens for X-ray examinations were prepared by filling these alloys, and these specimens were sealed in evacuated quartz tubes and giving beta phase homogenization treatment to release the strain effect and odor effect. These temperatures are also the same, and homogenization time were selected 15 minutes for both of the alloy sample. Powder diffractorams were obtained for all the specimens at the different stage of aging in a long time interval. This is an X-ray diffractoram taken from copper, zinc, aluminum alloy samples after quenching at the room temperature after long-term aging at room temperature for 15 years after quenching. As you can see, peak intensities are different, and this profile exhibits superlattice reflection. Also, at this diffractoram, these peak phase are important. These are 1 to 2, 202, 1 to 8, 208, 1 to 10, 2010, and others. This is another diffractoram taken second copper, aluminum, mangan alloy sample after long-term aging at room temperature about 15 years after quenching. As you can see, this diffractoram also exhibits the same character with this plane pairs. A series of X-ray diffractorams have been taken from both of the alloy samples in a long time interval, and some changes have been observed in the diffraction angles, peak intensities, and peak characteristics with aging. In particular, some of the successive peak space have shifted toward age others. These successive peaks provide the following relation for 18R Martensitic structures. Also, this plane pair can be listed as follows for 18R structures: 122, 202, 128, 208, 110, 2010, 040, 320, and others. At the long-term investigation, it is observed that these peak pairs come close each other with age and duration, and this change refers to the changes in the crystal structure of material. Also, this change refers to the rearrangement of atoms in the displaced disordered manner. This is the basal plane of the martensite, which has a rectangular shape, and with the martensitic transformation, the rectangular shape of the basal plane turned into the hexagonal shape. It is important that in the disordered case, we can take atom sizes approximately equal each other, and this hexagon becomes a normal hexagon. In the ordered case, lattice distribution is regular and neighbor atoms sizes are different, and a deviation occurs from the normal hexagonal structures. Second experimental study is performed on electron microscopy. And as you can see, electron diffraction pattern also exhibit superlattice reflections. Conclusion: shape-moment effect is evaluated by the structural change in microscopic scale by means of martensitic transformation. The fundamental structure of beta-type martensites are orthorhombic closed packet structures, which consists of an array of closed packet planes in coupled-based shape-moment alloys. The beta-type martensites have the layered structures and are characterized by the stacking sequences depending on the order in the parent phase structures. Coupled-based ternary alloys have the diotary-type superlattice structure in parent austenite phase, and the following stacking sequences occur with the martensitic transformation. Sequences are AB, CB, CA, CA, BA, BC, BC, AC, and AB for 18R martensitic structures. On the basis of austenite martensite relation, basal plane of 9R or 18R martensite originated from the 1 type planes of parent phase, on which lattice invariant shapes occurs into opposite direction with the martensitic transformation. These are the references, and thank you very much to listen my talk. If anybody has a question, I'll try to answer.
So, hi, I'm Zuhan Ma, and good day, everyone. Today, I'm going to talk about modeling of the swelling deformation of hydrogel and use deformation to further control the stem cell differentiation. So it is the background of this project. Nowadays, the hydrogel is a popular material used in biomedicine, and it has a very special properties like high swelling rate and high biocompatibility, and then it can absorb the water and swell. So the above mentioned properties makes the hydrogel has a similar behavior with the momus organ tissue. That's why we chose it as the substrate of stem cell in virtual experiment. And besides, it's by different production, it can carry and releasing the growth factor and medicine to help the stem cell growth. So in our project, we use the special particle to cause the wrinkle on the hydrogel surface. and the wrinkle will apply the stress on the stem cells, and it will be a mechanical stimulus to trigger the stem cell differentiate into different functional cells. So today I will mainly focus on how to control the wrinkle of hydrogel film by adding the special particles and building up the simulation modules to find out the optimized design of hydrogel film, which will be the best substrate for the stem cell differentiation. So here's the outline of today's presentation. Firstly, I will introduce the detail of how to manipulate the deformation of swelling hydrogel from preparing the special particle and use the particle to align in the hydrogel film by electrophoresis method. And after the particle is aligned in the hydrogel and swelled by the water, it will make a wrinkle on the surface. And then I will, second, I will talk about how to use the computational method to reproduce this behavior in the computer. I will talk about the theory and the methodology. Then we will combine these two experimental and simulation tool to find out the optimal design particle distribution that would be the best fit for the stem cell differentiation. Then is the conclusion. So let's start how to manipulate the deformation of the swelling hydrogel. So first we need special particles. The purpose of the particle that it can releasing the growth factors that help the stem cells. And the second reason is the most important reason. It can modify the mechanical property in the hydrogels. So that will cause heterogeneous property in the hydrogel. So it will cause the deformation on the surface. So let's start the preparation of the particle. So we will prepare a drug or the growth factor that will look in the green dots. Then we will surround them by the polymer. For example, will be PLGA and PVA. So after it's surrounded by the polymer, we will coat them by the reduced graphene oxide to make it have the electrical properties. Then we will coat the other layer of the polylysine, also known as the silk protein, to increase the biocompatibility that the stem cells won't seen as a attack cell or something. And then in the last step, we will coat the other layer of the graphene oxide to increase the electrical properties. So next step, we will use the electrode to control the particle alignment. So how to control the alignment of the particles? The first step, the particle will randomly place in the hydrogel film. Then we will apply the electrical film by placing the electron underneath the film. Then the particle will tend to cluster in the area where it's without the electron underneath. So the second row, you can see the confocal microscopy image is taken from the experiment. So the green dot is the particle, and it will distribute in the black. The black area is the whole hydrogel. So after that, it will align in the hydrogel. Then the third one is the real experimental theme that we use. Then, okay, yeah, after we finish the whole heterogeneous hydrogel film preparation, we will leave it on the electron. And then we will place the stem cell on the surface. So after the stem cell on the surface, we will apply the water and suck the hydrogel film into the water. And the film will start absorb the water. And during this progress, because the particle inside, so the swelling hydrogel will have a biomimic wrinkle, which look in the right-hand side of the slides. And the wrinkle will become the mechanical stimulus to the stem cells. And after we build up the experiment, we want to use the computational prediction to reproduce the swelling hydrogel behavior. And then the following is how we do it. So we use a theory called the deformation chemomechanically coupled theory. It's adopted from Chester. And it's a complicated question, but we just have to focus on two parameters, which is the gradient of chemical potential between the surrounding solvent and the dry hydrogel. And then is the change the volume fraction. So in every time increment during the calculation, the differences of the chemical potential between the surrounding solvent, which we use water, and the hydrogel inside will have a corresponding polymer volume fraction. So as the time increase, the gradient of the chemical potential will be lower, and as well as the polymer volume fraction will be lower as well. Element package abacus, and combined with the user-defined element to enable the theory I just mentioned in previous slides, and reproduce fusion in the polymer and the extremely large deformation of hydrogel. So the model setting and the boundary condition was summarized in the below figure. The size of the film is with the width 12 millimeter, length 12 millimeter, and the height is 0.14 millimeter, which is quite thin. And the film will consist of two parts. One is the pure hydrogel region we denoted as gel 1. And the other is a particle cluster area, which is denoted by gel 2. Then we apply a chemical potential gradient on the top of the surface, which is look like the orange cursor. So it will like water observe from like a water flow from the outside get into the inside area. And the restraint condition is quite complicated because based on the observation of the interaction between the hydrogel film and the electron. The 4 edges of the film and the area contact with the electron, where is gel 1 area. This region provide more adhesion to the film. So to capture this feature, we the 4 edges of the model will glue on the substrate, and the corresponding displacement in the relative direction will be fixed in the current model. And this is the material property we use in using the calculation. Here has the 2 type of hydrogel property due to the different concentration of particles. The first type was the pure hydrogel, which denoted by gel 1. And the second type was the particles cluster gel. We denote it by gel 2, in gel 1 and gel 2, which is the shear modulus and the diffusion rate. So the shear modulus of gel 2 was lower than the gel 1. It is because there's more particle in the gel. The hydrogel will cause the lower concentration of the polymer, so it will also lead to the lower shear modulus of the materials. Then the diffusion of the coefficient, since the particle occupy more space in the gel 2, so the diffusion rate of the liquid and the degree of polymer cross-linking will be lower, so there will be a lower diffusion coefficient in the gel 2. Then after we build up the experiment and the simulation, we are curious about how would the width ratio of pure hydrogel, which is gel 1, and the particle cluster hydrogel, which is gel 2, will affect the deformation of the hydrogel film. So here we designed the 16 patterns of hydrogel film. We select the 0.3 millimeter as our unit size, and the range of the gel 1 will be from 3 to 9 and increasing by 2 as the interval. And the range of gel 2 were from 1 to 7, and it also increased by 2 as an interval as well. So why we select 0.3 millimeter as a unit size is after the conversion test, we have to give an accurate, we have to have an accurate and stable solution. So the I should redo it again. So we designed the 16 patterns of the design. We have the combination of 4 different widths of the gel 1 with the 4 different widths of gel 2, and the gel 1 is from 3 to 9 and increasing by 2 as the interval, and the range of the gel 2 was from 1 to 7. Due to the experimental restraint, because the electron cannot be not that thin as possible, so the width of the gel 1 will be 1 scale larger than the gel 2. So, and the measured size is 0.3, and it was how we use in the abacus, and this size has caused the most stable and accurate solution. And here, after the calculation, here is the sneak peek of the result of 16 pattern of design. It showed the deformation distribution. The red color, which means it has the higher displacement in that area. The blue color means they have a lower displacement in that area. And because this is very different between the computational world with the real world experimental result. So next slide, we will explain we have to validate the computational result. So because the hydrogel is very soft and fragile, it is hard to apply the mechanical test on it. So we use the radius of curvature as a quantitative indicator of the surface stress. So the smaller radius of the curvature were related to the higher surface stress, and oppositely, the larger radius of the curvature were related to the lower surface stress. And of course, the initial size of both will be is identical. So it is acceptable to compare two of them. So now we'll look back to the result I just shown. By using the validation method, here we notice that the width of the lower width of the gel 1 or gel 2. For example, like in the gel 1. Okay, it's not working, sorry. So like if the gel 1 is 3 or 5, or the gel 2 is 1 or 3, it will yield the unstable and irregular wrinkle, which is not considered as a good design when you use as a stem cell substrate. Then we label the radius with the regular wrinkle patterns, and the pattern has the ratio of 7 to 5 of the gel 1 to gel 2, has the smallest radius of curvature, which is corresponding to the highest stress, and it by is as the optimal design of the stem cell substrate. And then we using the same design in the experiment design to test the accuracy of our prediction model. So after the whole testing process, the simulation result with the average radius of curvature is 1 millimeter, and the experiment result is 1.3 millimeter. The error of the model is 27%. But when you see on the side view of the both results, the wave height has 0.92 millimeter, and the experiment result has 0.9, which two numbers quite close, and the error is just 1.4%. So it demonstrates that the current prediction model can predict the overall configuration and the trade of the swelling pattern in the hydrogel film. So also in the experiment, we test the gene performance of the stem cells on the wrinkle, and it eventually has the higher score of the active protein that would tend to differentiate into the organ cells. So come to the conclusion, we build up the functional particle, and then we use the particle to cause the deformation of hydrogel, which the deformation can be designed. And also we reproduce the snake-like wrinkle, and we found the optimal design by FEM software. Although, because it is a very new project, everything is still immature, the relationship between the surface stress and the stem cell differentiate result should be studied further. And our future vision is to develop a database that can predict and control the stem cell differentiation. And it can fasten the whole experiment job and may be helpful in the medicine industry in the future. So thank you for the listening. And I'm sorry for the technical issue.
I'm a postdoctoral research associate at Indian Institute of Technology, Kanpur. Earlier, I was at IIT Hyderabad, India, but recently I joined Indian Institute of Technology, Kanpur. So today I'll be discussing about the introduction of my work. And the title of my presentation is Metal Oxide-based Nanostructure Material for Electrochemical Non-Enzymatic Biosensor and Energy Storage Applications. And today I'll be discussing about the introduction of these two applications, that is biosensor and energy storage, then the motivation behind doing this work, then the objective, then some results based on the experimental analysis and summary. So the need of energy storage devices, nowadays we are seeing that due to the huge amount of fossil fuel depletion and pollution, like global warming, acid rain, and also because of the limited non-renewable sources of energy, we require an energy storage devices which can convert, which can store charges, and which should, and it should be highly sufficient and sustain, and that energy it should be in the sustainable form of energy. So we know that there are a lot of energy storage devices like batteries, capacitors, fuel cells. So supercapacitor, it has come as the better source of energy storage devices because it is better in terms of power density, and it is also environment friendly. It means the electrode which we are using, that can be as an environment friendly electrode, and the cycle life of this device, it's very high compared to other two batteries and capacitors. Like here in this lagoon plot, we can see that the supercapacitor, it acts as a bridge in between the conventional capacitor and battery. So it has a limited energy density, but it has a higher power density. So higher power density means that it can deliver high amount of charges. So quickly I'll discuss little about the supercapacitor. So supercapacitor are three types. It is the EDLC, electrochemical double layer capacitor, pseudocapacitor, and hybrid supercapacitor. So EDLC, there is a deposition of electrolyte ions and the electrode ions, and in this EDLC there is a double layer. There is a formation of double layer at the electrolyte interfaces. Whereas in the pseudocapacitor, there's an interaction between these two ions, that is the formation of double layer, and then there is a redox reaction between these two ions. And in the hybrid supercapacitor, we see the combination of both the electrodes possessing different kinds of mechanisms. So the challenges for supercapacitor is it has a low energy density and it's very costly. Then the self-discharging rate, and industrialization has become the major problem for supercapacitor because of the limited commercial product, lack, poor performance, then the electrode structure, then the electrode material. Another chemical application on which we are working is amperometric glucose biosensor, and it is a integrated device which measures the change in the current due to the oxidation or reduction of an electroactive biological element, and it gives the sensing of conversion of glucose to the gluconactone. So the need of electrochemical glucose sensor is it monitors the blood glucose level, then it reduces the risk of complication during diabetes, then it should have the potential ability for the real-time and on-site analysis, and it should be highly selective and sensitive for the glucose sensing. Now, though there are so many materials which can be used as an electrode for the electrochemical measurement of glucose sensing and energy storage devices, but we have focused on since there are so many challenges like the high solubility of the electrode material, then the less conductivity of the electrode material, and its structural design. So the measures which we have used here for overcoming these challenges is, firstly, we have selected transition metal oxide as an electrode material, and we have done some chemical modifications like hybridization and defect creation so as to enhance the properties of the transition metal oxide electrode material. Now, transition metal oxides we have used because it has an unfilled d orbital, so unfilled d orbitals, and it is in various structural form. We can synthesize it in various structural form. Then it is easy to synthesize, and it has we can modify its morphologies also. As morphology and surface area, we know for electrochemical application, it is a very important parameter. So we can modify accordingly. Then it's low cost and it is abundant in nature, and it is also less toxic compared to other materials. And from other literature, we have seen that its cycle life is also high. So the So the objective of this work is synthesis of transition metal oxide nanomaterials with different morphologies, then the fabrication of electrode for electrochemical application, then the electrochemical properties like supercapacitor and glucose sensing measurement, then the study of these two modifications, hybridization and defect creation. So the first work is the hybridization of cobalt oxide and manganese oxide nanostructure for high performance glucose sensing. So we have used hydrothermal method for the two-step hydrothermal method for the synthesis of alpha amino 2 nanorods, and again we have modified it by depositing CO3O4 nanoparticles over alpha amino 2 nanorods. Now the electrode we have fabricated using a carbon paper, 1 × 1 centimeter carbon paper, and we have deposited MnO2 CO3 slurry over the electrode to investigate the electrochemical properties. So first, for confirming the structural properties, we have done the Xrd, and we can see here that the material is pure. We have also conducted the ritual refinement so as to know the other lattice parameter of the material, and it has come as a tetragonal phase of the alpha amino 2 nanorods. Then we have also conducted the Xrd of the alpha amino 2 CO3O4 hybrid nanomaterial, and we are seeing that the material is in pure phase. This is the morphological studies of the hybrid nanomaterial and amino 2 nanorods. So this is the HRTM image of the amino 2 nanorods, and these are the for the hybrid nanomaterial. And here we can see that the CO3 nanoparticle has been deposited over alpha amino 2 nanorods, and these are the sad pattern and lattice fringes, which confirms the structural confirmation structure, which confirms the structural parameter of the hybrid nanomaterial and amino 2 nanorods. So BET we have conducted to know the surface area of the material, and we can see that the amino2 is given 11 meters square per gram mesoporous nature of the nanomaterial, where after characterization, and we are seeing that the alpha amino 2 nanorods, this is a red curve is for the alpha amino 2, and it is potentially it is potentially silent in the electrolyte, whereas the CO3O4 nanoparticle, it is active, and the combination of these two nanomaterials, it is giving a high oxidation rate for the hybrid nanomaterial, and the oxidation potential is 0.25 volt. So for the chronoamperometry measurement, we have fixed this potential 0.25 volt for the chronoamperometry measurement. And here we are seeing that by continuously successively adding this 60 micromolar of glucose. First we have done for CO3O4 electrodes, so as just to compare the results. And here we are seeing that the material is giving a continuous enhancement in the current. So the sensitivity is calculated as 0.136 microampere per millimolar per centimeter square, and the linearity has been maintained up to 720 micromolar. Whereas in the case of hybrid nanomaterial, we can see that the sensitivity has been enhanced to 127 microampere per millimolar per centimeter square, and the linearity has been maintained up to 7 millimolar. So this shows a huge enhancement of the sensitivity and the linearity of material because of the hybridization or combination of two nanostructured materials. So later, for knowing the real application or suitability of this electrode for the real application, we have conducted the blood and serum sample, and we have compared the results with the pathology centered pathology data and also with our data, and we are seeing that the material is giving an approximate same current value after injecting a glucose, the glucose. So this is the interference test, and we are seeing that the material is giving higher sensitivity for the glucose. Like in blood, there are other materials are also present, like ascorbic acid and uric acid. So interference test has been done to see whether the material is suitable for glucose sensing or not. So here we can see that it's giving a higher sensitivity towards glucose. Now we can see from the other reported literatures, and we can see that the material is giving a higher sensitivity with the linearity of 7 micromolar, and the detection limit is also very low, that is 0.023 micromolar. Now another material that we have selected is tungsten oxide, transition metal oxide. And tungsten oxide, we have created a defect in tungsten, that is oxygen vacancy in tungsten oxide. So it has become as W18O49 nanorod. Again, we have used solver thermal method for the synthesis of the nanomaterial, and the same process for the deposition of this nanomaterial over the carbon paper electrode. So first we have conducted the structural characterization Xrd, and we are seeing that the material is in its pure form. Now the XPS for confirming the proximity of oxygen vacancy, and from here, from the oxygen deconvoluted peak, we can see that the material has an oxygen vacancy. So this is the morphological studies of the W18O49 nanomaterial, and here we are seeing that the bundles of this nanorods has been formed, and these are the HRTM image, SAT pattern and lattice fringes, which confirms the single crystalline growth of the nanomaterial. So this is the BET isotherm, and it is showing that the material is giving a high surface area of 82.309 meters square per gram with a pore size distribution. This distribution is due 2.4 nanometer. So this is the first we have done. We have used this material for the energy storage supercapacitor application. And from cyclic voltammetry, we are seeing that the material is giving a pseudocapacitor nature by showing the redox peak of oxidation peak at 0.18 volt. And here we have calculated the specific capacitance, which is 470 milliampere hour per gram at a minimum scan rate of 1 millivolt per second. Now we have conducted the galvanostatic charging discharging measurement so as to know the charging discharging properties of the material, and it is approximately 452 milliampere hour per gram at a current density of 1.25 ampere per gram. So here we are seeing that here from this GCD and cyclic voltammetry curve, we can see that the material is giving a properties of pseudocapacitive battery nature. Generally in pseudocapacitive, in like supercapacitor, we are seeing that the GCD pattern is in triangular features are visible. But here we are seeing that there is a potential drop from 0.8 volt to 0.4 up, that is an IR drop. So this confirms the presence of the battery feature in the nanomaterial. Now we have done this stability test and impedance spectroscopy for knowing the resistance in the material, and it is 1.40 and 1.13 ohm. This we have done from the circuit fitting model analysis, and also we have conducted the stability up for 2000 cycles, and this is showing the material is its capacitive retention is 87.5%. So the mechanism that we have understood from our analysis is the oxygen vacancy. It acts as an active site for the electrolyte ions to uniformly propagate or uniformly interact with the electrode material. And the one-dimensional nanorods has a more number of active sites. And this agglomerated form, it gives it agglomerated spherical bundles of this nanorods. It provides a spherical. The surface provides a high surface area to the nanomaterial and also to the stability. So this is the comparison of the energy storage performance of the other transition tungsten based materials. And here also we are seeing that we have used 1 molar H2SO4 for the energy storage measurement, and this is giving a higher specific capacitance in a large potential window of that is minus 0.4 to 0.4. This is the glucose sensing applications of the same W18O49 nanomaterial. And here we are seeing that the material is giving in 60 micromolar glucose, it is giving a huge, it is giving a oxidation peak. And with the increase in the scan rate, there's no shift in the oxidation peak. So which gives a stable performance of the nanomaterial. Here we can see that without glucose, this material is curve is like this. And after giving 60 micromolar glucose, there's an oxidation peak as an I. So this signifies the ability of this material for glucose sensing. Now this is the amperometric response of glucose sensing, and here we are seeing that the material after adding 60 micromolar of glucose, by successively adding 60 micromolar of glucose, it is giving a sensitivity, and a continuous enhancement in current can be seen till 2 millimolar, and the linearity is also being maintained with a R of 0.98401. So the sensitivity has been calculated at 167 microampere per millimolar centimeter square with a very low detection limit of 0.02 micromolar. So interference and stability test has been done, and this is again after 7 days of stability, the material is giving a stable performance, which shows the real use of this material for real blood and serum sample. This is the comparison of this material with other reported literature, and here we can see that this is giving a higher sensitivity. Now, we have known that the W18O49, after doing the energy storage characterization of this material, we can see that the W18O49, it is not very stable. It has been run for 2000 cycles, and we can see that the 87.5% of capacitive retention is there. So now our next purpose is to improve the performance of W18O49. So we have thought about RuO2 nanomaterial. The motto of selecting RuO2 nanomaterial is first to enhance the stability of W18O49, and second, since we have used H2SO4 and acidic electrolyte for the W18O49, we wanted a material which goes well with the acidic electrolyte, and that is the main purpose of using RuO2, because RuO2, like as we have read and understand, that it is behaving very like it's giving a good current and good stability in the acidic electrolyte. So the RuO2 for enhancing W18O49 energy storage properties, it is a pseudocapacitive material, and it's had a high conductivity, and its theoretical capacitance is also 1450 farad per gram, which can be a good solution for hybridizing it with W18O49. So we have first used solvothermal process for the synthesis of W18O49. Again, we have used a hydrothermal process by dissolving this W18O49 in the water, and then again we have added ruthenium oxide precursor in the solvent, and then we have used hydrothermal process for the synthesis. So this is the Xrd, and we can see that this is for the W18O49, and this is for the hybrid nanomaterial, and we can see that this amorphous ruthenium oxide has been formed by suppressing the peak of 010 W18O49 nanomaterial. So this is the XPS characterization to confirm the W18O49 and the proximity of oxygen vacancy, then ruthenium Ru3D states, and then W5+ and 6+ oxidation states. So this is the morphological states or studies of the W18O49, the nanorods formation of W18O49, and this is for the combination of W18O49 and RuO2. And here we are seeing that the RuO2 nanoparticles has been dispersed over the W18O49. This is showing the formation of RuO2 amorphous nature as well as the little crystallinity of W18O49. This is the BET isotherm, and the W18O49 is giving 82.309 meters square per gram of surface area with a pore size distribution of 2.4 nanometers, whereas the hybrid material is giving a huge double enhancement in 149.698 meters square per gram. So this shows that after incorporating a ruthenium oxide nanomaterial in W18O49, there's a huge enhancement in the surface area, which can assist the electrode material to get well with the electrolyte. Now the electrochemical characterization for energy storage we have conducted, and we can see that the W18 RuO2 nanomaterial is giving an EDLC behavior as a rectangular pattern. The W18O49 is giving a pseudocapacitive nature, pseudocapacitive battery nature, and this is giving again a large surface area of the combined material. So from cyclic voltammetry, we have calculated the specific capacitance, and the highest specific capacitance is 1126 farad per gram at 1 millivolt per second of scan rate. So this is a charging discharging, and we have already seen the charging discharging of the W18O49 nanomaterial, and it is like the pseudocapacitive battery nature. There we can see that the potential drop from 0.8 volt to 0.4, but here in this case we can see the triangular pattern of the hybrid nanomaterial. So the mechanism behind this, okay, first let's the specific capacitance has been calculated from GCD is 1050 farad per gram at 1 ampere per gram, and the stability we have done till 3000 cycles, and the material is giving a highly stable nature. So our purpose is to enhance the stability of the material, and it has been enhanced for 3000 cycles. It has been enhanced up to 92% of stability. So there's a huge enhancement in 3000 cycles. This is for the comparison. We have also conducted W18O49, and here we can see the rectangular pattern of RuO2 nanomaterial, and the specific capacitance is 582 farad per gram. So the W18O49 hybrid electrode, we can see that due to the incorporation of ReO2 nanoparticles, and the increase in the surface area, the material is giving high electrochemical interaction of ReO2 with the electrolyte material. And we can, from there we can see that there's a change in the mechanism from W18O49, which were giving a mechanism of pseudocapacitive battery nature. After incorporating ruthenium oxide nanomaterial, the material has been changed to ETSA, complete supercapacitor properties. So this is to enhance the properties. Here we can see that the W18O49 is giving 452 milliampere hour per gram of specific capacitance. Ruthenium oxide is giving 812 farad per gram of specific capacitance, and W18O49 hybrid nanomaterial is giving 1126 farad per gram of specific capacitance at a scan rate of 1 millivolt per second in the same potential window. So this shows that the hybrid nanomaterial, because of the augmentation of this nanoparticles, or because of the synergistic effect of W18O49 and ruthenium oxide nanoparticle, this hybrid material is giving good properties. So this is a summary. Here we have synthesized this nanomaterial, manganese oxide, cobalt oxide, and the hybrid nanomaterial, then the oxygen vacant tungsten oxide, then the ruthenium oxide, and then the hybrid nanomaterial of tungsten oxide and ruthenium oxide. And we have investigated the electrochemical supercapacitor application of tungsten oxide and this hybrid nanomaterial, and also the electrochemical glucose sensor application of CO3O4, MnO2 hybrid nanomaterial CO3O4, and then W18O49 nanomaterial. So thank you so much.
Also, this is indeed, of course, somewhat related to my first talk in this webinar, and it's also in a way also a hot topic in material science. And I will go into a little bit the basics of the soft materials, but also a little bit background in nanotechnology historically, as well as self-assembly, which plays a key role in this particular field. And if we take a look at the first slide here, soft materials and machines, those four hairy gentlemen that you can see there is actually a band. Excuse me, it's an old band that is called Soft Machines. That's their name. I wish I had their music here in the background, but on a short notice I cannot come up with that music shortly. Anyway, so this talk is organized as in the following way. I will talk a little bit about nanotechnology, that is to say radical nanotechnology. Then I will go into evolution and materials, since the evolution itself tells us about the experience that we have already when it comes to soft and hard materials. And as we all know, we have a certain kind of biomimetic thinking is very present today in engineering and the natural sciences, and biomimetic thinking in terms of what can we learn from evolution, what can we learn from nature, is most definitely beneficial when it comes to the materials development. I will go into that the physical laws look different at the nanoscale. Self-assembly, I mentioned that already, is a key thing to the key concept for developing soft materials and using them. Soft materials, yeah, especially in robotics, it is something promising that we can use soft materials. I will go into that also. Now, let's start a little bit to talk about the so-called radical nanotechnology. Here on the next slide, we have a, let me see. So Eric Drexler, he is one of those technological visionaries. He wrote a book called Engines of Creation. It's actually quite old book by now. He has been, he coined this idea about self-replicating assembler, as well as, well, let me put it like this. We know from nature that we have molecular motors and cellular machines, and in nanotechnology, they try to replicate that, to try to copy it and make self-replicating assembler out of it. That means small robots that can make even smaller robots that can even make even smaller robots. And that is basically the safe self-replicating assembler. We have different kinds of, when it comes to molecular motors, a ribosome in the cell is a good example for a molecular motors using the mRNA to make new proteins. As you can see here in the top, amino acids are being generated in this way via the mRNA and a ribosome small unit, and we can see also the growing peptide change. So Richard Feynman is another guy. I know that you guys know him, of course. He is also having ideas about nanotechnology and fabrication and materials. He states that he thinks that it's physically possible to build up materials and things moving atom by atom. That is controversial, of course, but it is one idea that is well alive in the nanotechnology and nanomaterials community. And those robots, the nanobots or the self-replicating assembler of Mr. Drexler, is the ones who are supposed to put the atoms together into new materials. Here is a couple of examples of radical nanotechnology, a molecular propeller and a molecular planetary gear. It is yeah, so those are they don't exist yet, but there is great effort to go into this further. A molecular assembler has also, in theory, been designed like this: that you have a fine motion control nano assembler that can basically, from the bottom to the top, as you can see here, we can have a look at. Wait a second, at this picture also. It can move atoms and place them at places where we want them to have to be, and we can even make a factory out of this, a Drexler factory replicator that can make nanomaterials even on a chip. So it is a little bit like brewery, right? You can, as long as you have your self-replicating assembler that can put atoms together at places where you want them to be, they just need the raw materials to do that, and you put them into a container and off they go. What else can I say? Radical nanotechnology also includes fixing things at the cellular level in your body. So those nanobots can go in and well, as I wanted to point out this again, it's a future scenario, right? Even though research is being done in this field. So the nanobots at the medical level, they can repair DNA faults and also mistakes that are happening in the at the cellular level, repairing directly cell membranes, etc. in the body. Let me see, cryonics, I think I will skip that. I can just, a part of the radical nanotechnology community is also cryonics. I'm not sure if you guys have heard about that. Cryonics is almost like a philosophical or maybe even pseudo-religious thinking, which they have the opinion if we can freeze our bodies down after we die, and so our bodies can be preserved for the future. Then in the future we can be, so to say, we can, so to speak, resurrect from the death. And one part which is important here is that the nanomedicine and nanobots will sort of repair the damages caused by freezing. This is very, very spectacular, and of course not based on any kind of sound science, but it's worth to know that thoughts are being made in also in those directions. There are many kind of things in those way. Ray Kurzweil is also a nanotechnology thinker. In the 2030s, nanobots in our brains will make us godlike, he says. Once we are cyborgs, he says, we will be funnier, sexier, and more loving. I'm not sure if that is true, but anyway, this is the background when it comes to nanotechnology, as well as the thing that we have that I'm talking about today. What else can I tell you? I should maybe make a little jump here. We can talk about many things. What I'm heading at is soft materials and hard materials. Why is this something interesting? Well, before I continue, the reason why I have a little look at in the background when it comes to nanotechnology is, of course, that it is presenting a way of building materials from bottom up by placing atoms next to each other using nano robots or nano self-replicating assembler. So that is so-called robotics pick and place, right? You pick something and put it at a place that you want to have it, and undoubtedly so we're not there yet, that should also be contrasted to other methods such as self-assembly that we have in nature all over. Anyway, let's jump into the soft material versus hard materials and what we can learn from this. Here you can see this is a typical very hard material in the form of a locomotive, and a horse is soft material, of course. And we have many different kinds of materials in nature, feathers, and so on and so forth. So we are actually have soft materials all around us. And if we look at this timeline, here is the formation of the Earth. And if we go over way back to where we are, where humans came alive, I almost said here, we have a development, and it's kind of it is interesting to see what kind of development we have throughout evolution, because that means how much, that is a measure for how much knowledge does nature have when it comes to materials, and that is of course a knowledge that we can use for our purposes. So if we look at this time scale here, the first living things are around here 2.5 billion years ago, and there are cells with nucleus, and there is also here a rise in the atmospheric oxygen, and later on dinosaurs, etc. But what is here important is to know that in this period of time we only have soft materials, soft living beings, cells and small animals, insects and amoeba and things like that. Here at you see in the Phanerosauric period, it's the first hard-shelled animals that comes up. So one must argue like this: in terms of evolution, soft materials is the normal thing to have, and hard materials is not. Here is actually the good picture of the first animal that has some kind of hard material inside. I actually forgot its name now, but I think it is it's not a microorganism, it's more like an insect. And here is the conclusion out of this: soft materials, or soft machines, because every cell has also molecular motors and cellular machines in order to function. Soft materials or soft machines were dominating life or everything on Earth for roughly 2 billion years. So that is the difference between soft materials and hard materials in terms of their presence on Earth. And so it is undoubtedly so that the evolution has not been in the hard materials field, but rather in the soft materials field. So that is, yeah, and therefore I think it is interesting to compare soft and hard materials for different kinds of applications. And one thing is, which is obvious, is robotics, which kind of materials you can use in robotics, as well as in other neighboring fields such as sensors also, and things like that. And yeah, I have to apologize that I don't have the videos available here, but what I can tell you about here is a quite big robot which is based upon hard materials, and I simply have to tell you what's in this video that we cannot see. This robot is made of hard materials. That means that it stumbles and it falls and it's not rigid, and it is rigid but not flexible, and cannot bend and cannot adjust in the same way to the environment and environmental demands. Quite in contrary, if you look at fish, fish is soft and smooth and swims in various flexible ways and can adjust to the environment accordingly. Here, this has also been used. Here we also have videos that is not available on my equipment now. Those soft devices, for example, pacemakers can be made in different ways. Here's the first hard ones, and here is a soft material pacemaker on the bovine's left wing and right ventricle made of PZT. So in this case, we can see also a comparison here. On the one side, we have the hard materials, stainless steel, aluminum, metals, and ceramics, and so on, for pacemakers as well as robots. On the other hand, we have soft fish and soft flexible electronics that can be used in different ways. And yeah, so since soft materials are so kind of just very well, we can talk about, we have an embodied intelligence of soft materials. There are many different kinds of soft materials. They have a big range, coming from having Young's modulus as tiny as kilopascals up to terapascals. And brains and fat and hydrogels are in this range. PDMS, skin and ears and heart tissues are here in the megapascal range. Tibia bones and so on, glass and steel, then we are talking about terapascals. But you see, there's still quite high flexibility compared to, as combined with Young's modulus. I wanted to tell you something about different physics at the nanoscale, because that is what we need to know about when we want to design as well as build the nanoscale materials. So the two, some of the most important things are at the nanoscale compared to the macroscopic scale. We humans tend to believe that the nanoscopic scale is basically just like the macroscopic scale, but smaller. And that is, of course, not the case. At the smaller nanoscopic scale, we have Brownian motion, which is in principle thermal energy. We have the surfaces that we normally think are smooth. They are very sticky and rough at the nanoscale. Water is not as fluid as we think. At the nanoscale, it is like syrup. It has an extremely high viscosity. And when it comes to, so this is the environment that we are dealing with when we are talking about making soft nanomaterials. Brownian motion causes nanoparticles to conduct a random walk, just like this, right? Small things go fast, but they don't go very far. And they also have a non-directionality. That is to say, it is truly random. That is how how things work at the nanoscale. Let me just think a little bit here. So I have to. We can also, this is not only a drawback, we can also design surfaces, sticky surfaces. We can design particles with sticky and non-sticky patches in order to make them stick to each other and self-assemble into materials that we would like to have. And here again, as I said, water is like syrup, and the at the nanoscale, at the macro scale, we are dealing with inertia. At the nanoscale, we have viscosity and layer of friction and stickiness. Let me see. So material strength depends on size, and flaws and microcracks on the macro scale induce materials failure. But that is not the case at the nanoscale. Now, what I was talking about earlier, how to build nanomaterials on the nanoscopic scale using pick and place atom by atom is, how should I say, is a visionary idea that has not really been implemented or investigated, but self-assembly has been investigated to a great deal, and that is a parallel process that makes entities, be it molecules or atoms, move in a coordinated way, and molecules and building blocks in general. You remember maybe that I was talking about viruses and viral entities that can be put together via biomolecular architecture. And the same way goes for soft materials in this case, that they self-assemble into increasingly bigger materials. And that is to say, the preferred manufacturer method here in this case is most definitely self-assembly and not necessarily robotic pick and place. So beyond self-assembly, when we use self-assembly, when we also apply sorting and different sequences of sorting and mixing of the building blocks, we can end up by constructing as well as using for this purposes soft machines. I have to have a little bit of a little look here. I cannot say, so those are good. Why can we say that soft machines is at all doable, that we can make them? Well, nature tells us that they are, because in nature, in the cells, we have molecular machines such as the chaperone that organizes by using ATP as an energy source into properly folded proteins, as you can see here, right? So this chaperone, which all different kinds of cells have, is a molecular machine, a synthesis machine, if you so wish, with the use of ATP, which goes over in ADP, you will fold the protein. Another molecular motor is ATP Synthase, which also uses ADP and ATP, and it is a hydrogen pump in the cell membrane. So saying this, having this said, we know that molecular machines and soft molecular machines and soft materials are possible simply because of the evolutionary advantage that we have, the evolutionary time advantage that soft material has, and nature has, so to speak, had longer period of time to develop soft materials versus hard materials and soft machines versus hard machines. So the promising way to take, the promising path is to have an evolutionary perspective on materials, and if we do that, we can see that the experience and knowledge about soft materials and soft machine is so much bigger than when it comes to hard materials and, if you so wish, hard machines. So the take-home message in this talk is maybe nanotechnology, futuristic scenarios, they remain vision. Evolution, I should point that out, also takes place predominantly on the nanoscale. I'm sorry that I didn't point that out earlier. So it is not only that soft materials are predominant throughout evolution, but also it happens at the nanoscale. It is inside the cell. We are talking about a cellular evolution and so on and so forth. And as I said earlier, soft materials have been known or have been a part of evolution since over 2 billion years. Hard materials occurred 0.5 billion of years ago. That is a big difference. So the inherent knowledge in nature when it comes to soft materials is much, much bigger, and we can learn from that. So rather biology than macroscale engineering. I think I can just say that. Self-assembly and beyond may be viable of advancing nanotechnology of making soft materials and soft machines, and that is something that I already explained. So I hope that you understood what I was talking about. I have a little problem with my slides here, but since they are all connected together, but I believe you can see what I am saying. Thank you very much for your kind attention. Thank you very much.
Yeah. So good evening to all. Today, my name is Nadugopal Manna. I am a senior research fellow in CSIR NCL, Pune, India. So, and first I would like to thank the Global Scientific Guild for giving me the opportunity to present my work. So today I'll be talking about the a catalyst that for oxygen evolution reactions. So my title of my presentation is the nickel iron layer double hydroxide nanoparticles decorated over the nitrogen doped entangled graphene framework for oxygen evolution reaction electrocatalyst. So first, before going to the catalyst development for oxygen evolution reaction, which is very important for electrochemical water splitting, I'll go through some brief introduction. So why we are doing that electrochemical water splitting and the importance. So it is a kinds of energy devices. So why we need energy devices? If you see in the Rice University recent studied the humanity can suffer the top 10 problems from the next 50 years, which is associated with the energy, water, food, and the other population democracy. So still we are living in the 21st century. So we are going through the various kinds of problem, but the energy is among the top problems associated, because we all across the globe where we are staying, but we all need the energy to survive from various purpose. So among them, like transportation, portable or stationary, or the other these are the primary things we need to make it mobile for a various sector. So all these energies are coming from the various sources like coal, hydroelectricity, renewable energy sources, and the natural gases. If you look into the percentage of energy we are getting from the various sources like coal, which is giving almost 59% energies we are getting from the coals, which is a carbon based fuel. So based on the that coal burning, there are tremendous issues coming like the greenhouse gas emission, the carbon dioxide, which is having 81% carbon dioxides are coming from the burning the coal. So effect of the that global greenhouse gas emission in various form of the state, like solid water or the gas phase, like air, water, as well as the solid phase, various pollution is creating. So which could be a future can different kinds of problem could arise. So based on that, now the research in global wise, the various energy sectors, they are focusing on various renewable energy sources, so like wind power, geothermal power, tidal power, or biofuels. So various energy sources are people are focusing, and they are doing a enormous research has been done. But only one kind of device cannot solve all the problems. So we need other source, there is a issue with the renewable energy sources because of it is an intermittent nature. So then we cannot focus only the single source. So we need to store this energy to other way like energy storage and energy convert to another fuel. So that directly it can convert to using the various sun or solar systems, or the various geothermal energy to convert to the water splitting, and that could store in the form of the chemical energy like hydrogen, or it can store in the oxygen, and which can further use for various purpose like the transportation, portable or stationary systems. So based on that, here in my work I am focusing on the electrochemical water splitting. So if you look into the importance of water splitting, like which is forming a overall water splitting, here hydrogen and oxygen is formed, because that hydrogen has enormous interest, because hydrogen having the specific energy which is very much high compared to the currently available fuels which are using for various purpose. But the problem in the hydrogen is the which is coming from the various carbon based fuel burning and the combustion. So the natural gas which is coming 48% coal, 18% and oil is 30%. But the electrolysis process getting hydrogen is very much less amount, like 40% of electrolysis process are giving the hydrogen production. So if you look into the overall electrochemical water splitting, where the cathode hydrogen, the proton to form hydrogen, and the anode oxygen, water to form oxygen evolution reaction. So the overall reaction in alkaline condition, there are two way it can form, like acidic condition and alkaline condition. As in this my work, I am very much interested about the alkaline solution. So here in hydroxyl ion form oxygen to potential minus 0.40 volt, and then this water can further in 4 electron process from the hydrogen. So overall reaction is the water to hydrogen and the oxygen formation in the potential minus 1.23 volt. So this if you see this reaction, kinetics is suffer because of the oxygen kinetics, because here you can see the hydrogen is your only hydrogen single bond form, but in oxygen formation it requires two double bond between two oxygen. So that because of the kinetically inert of the oxygen electrochemistry, the overall reaction process is very slow. So we need a particular catalyst to develop the to make the process very faster. So if you look into the precisely the mechanism of the oxygen evolution reactions, that it goes through 4 electron process with the various intermediate step. First step is the metal in alkaline as well as in acidic condition. First form the metal hydroxide, then it from the metal oxide and the metal oxyhydroxide, and this is a completely cyclic process. Metal goes through various intermediate step, and finally it is from the metal and the oxygen evolution. So still now the theoretical studies and few experimental studies suggested that the oxygen evolution reaction most active catalyst is the ruthenium oxide and the iridium oxides, so which having the optimum binding energy through metal, and the other intermediate having the optimum binding energy giving the best activity for oxygen evolution reaction. So but the challenging barrier on these devices for oxygen evolution reaction is that as ruthenium and iridium is a noble metal systems, so that because of the high cost of the electrocatalyst, and secondly is the long term durability, because in the oxygen evolution reaction is happening in 1 molar KOH, so that is at higher pH there is a more chances of the corrosion of the noble metal, and the whatever the other reactant bases like CO, and that can adsorb over the particular surface, it can affect overall durability of the electrocatalyst, because it having the 4f orbital, f orbital, sorry, not f orbital, 5d orbital, so which can easily binding through the CO and other contamination present in the in water systems. So the common challenge that associated that high cost of the electrocatalysis and long-term durability, we are focusing on the various non-noble metal-based systems. So among the various non-noble metal-based systems, the layered double hydroxide has a greater advantages compared to other systems, because here you can see the layered double hydroxide, that hydroxide are forms in the layer form, so there is a space between the two layer. Here the water molecule have the and as well as the hydroxyl ion can intercalate, and all the active center can be associate or participate through the overall oxygen evolution reactions. So there are advantages of the layered double hydroxide, which is very low cost, as well as it is a well developed material for oxygen evolution reaction. But the limitation associated with the layered double hydroxide materials is that poor electronic conductivity. It is only a double hydroxide, so there is a active center is enough numbers of active centers are there, but conductivity is very less. And second thing is the passivation layer formation, because in oxygen evolution condition, as there is a potential and the pH, both the condition is completely harsh condition, so there is a chance of after certain cycles the passivation layer formation, which can suppress the activity. And third thing is the particles agglomeration, because the layered double hydroxide having a particular size, so without any support systems there is a particle charge, as the individual particle having a certain charge, so there is a interaction and that can form the particle agglomeration during the due to the charging. The second thing is that only a layered double hydroxide, only a oxide or hydroxide systems can not sustain for a long time. So based on the current advanced research on the carbon support, we could see the any kinds of carbon support can use. So here you can see the various carbon supports already developed in the like from the 0 dimension to 2 dimension, 1 dimension, and 3 dimensional support already developed. So that is among them there are graphene based systems are well developed material. So after the getting the Nobel Prize on the graphene, so there are lots of work has been done, but further doping any kinds of hetero substrate on the graphene further can electronic property can be tuned. So here you can see the defect can possible in the dopant or age or the defect. So then that is electronic modulation. So second thing is that various heteroatom can be doped, like boron, phosphorus, tin, iodine, bromine, or but the thing is that theoretically and experimentally, if you see that experimentally and the theoretical value, so nitrogen doping shows the better electrochemical better electronic property modulation. So nitrogen could be a better option, nitrogen doping could be a better option over the carbon substrate. So but further nitrogen can dope in the graphene in various form, like as the graphene during the nitrogen doping, it can form the pyrrolic, pyridinic, or the types of quaternary nitrogen, various form carbon can be doped over the graphene substrate. So based on that, the activity as well as the durability can alter. So this is the graphene nitrogen doped graphene substrate, but still there is a issue is that when we are going for the graphene substrate, graphene is not a still now the available synthesis procedure. There are commercially available procedure. There are more than or one layer can form. So during the electrochemical performance, there is a possibility of the restacking of the graphene individual layer, so that can suppress the performance during the electrochemical condition. So based on that, here is our methodology how we are doing that. First we check the how metal part and the support can interact, and how the electrochemical property and can tune through the electronic property tuning. So here you can see in this one journal came in science, so there they have tried to summarize how the metal support can be tuned for better performance. One is the increasing the intrinsic activity by tuning the morphology of the in catalyst, and second thing by increasing the number of active sites by using a particular supports, and as well as tuning the morphology. So here in this work we have gone through this way, like increasing the number of active site using the metal particles, and using it our unique support like 3D morphology. So here 3D morphology importance is that 3D morphology we have prepared from the graphene oxide having the two-dimensional structure, three-dimensional structure. So their three-dimensional structure, their individual sheet are connected through a particular angle, which we called a nitrogen doped entangled graphene, because their individual sheets are connected through a entangled form in a particular angle, and there is a porosity. That porosity could help, because in oxygen evolution reactions, the oxygen as a gaseous product is formed from hydroxyl ion. So that hydroxyl ion mass transportation as well as the oxygen form, which should be removed from the active center. So here we from the 3D structure, here is a uniform porosity are there, which will be helpful for better electrochemical performance. So we have applied the freeze drying method to form the 3D morphology, and the 3D graphene. Another important is that thing is that the individual sheet can be act as a metal anchoring site, and there is a porous channel which could helps to better electrochemical surface area, as well as as graphene having the high electrochemical electrical conductivity, thermal conductivity, and due to presence of the graphitic structure of the graphene, so it helps to the better corrosion resistance. So which further helps to triple phase formation during the electrochemical performance. So here is our synthesis. First we use the graphene oxide as a substrate, then we use nickel acetate and the iron acetate in particular pH condition around 12, using the ammonium hydroxide, which can act as a reducing agent for metal precursor, as well as the nitrogen doped, and as well helps to the self assembly structure formation for the 3D structure. So first we have sonicated it for a long time, around 10 hours, so metal particles are entering. After that we hydrothermal solvothermal treatment for 180 degree for 12 hours, and after that we have applied the freeze dry condition. This is a very important things, because most of the cases after solvothermal or hydrothermal treatment, we used to go for the only filtration of this material, but here to retain the structure of the 3D structure, we applied the freeze drying. So freeze drying is a condition where at low temperature around minus 50 degrees centigrade, we just applying a vacuum pressure. So here whatever the structure is there, water molecule is there, it will remove, but the structure will retain. So first in this hydrothermal or solvothermal treatment, so metal particles nucleate over the nitrogen doped, because here ammonia, presence of ammonia, nitrogen can doped over the individual sheet, and their nanoparticles are oxides or layer double hydroxide grown over the particular sheets, and the structure will retain because ammonium hydroxide having a particular concentration, so self assembled structure will form. So only by applying the freeze drying, water could remove, then the 3D structure will retain. So final product is the nickel iron layer double hydroxide supported nitrogen doped entangled graphene framework. Further we used it as for the electrochemical performance measurement for oxygen evolution reactions. So to know the whether structure is formed, so we have done various physical characterization like FESEM and TEM image. So FESEM is a micrometer range. We can analyze. Analyze the structure of the graphene sheet, because graphene having the more than nanometer range, like micrometer scale structure. So here we have first checked the nitrogen of entangled graphene to know the exact morphology formed for the 3D graphene. So here you can see by applying the freeze drying method without any metal substrate adding. Here you can see that without any metal substrate, first we checked the whether nitrogen of entangled graphene. So you can see here the morphology is formed, that entangled structure what we predicted schematically, that is formed, and the individual sheets are connected through a angle, and the uniform porosities are there. In presence of nickel iron layer double hydroxide, so similar morphology is formed, porosity also retained, and the entangled structure is formed. But as I already told that there is an importance of the freeze drying method. So here we have done without freeze drying, applying just direct filtration of this material. So here we avoided these steps. Just after the solvothermal treatment, we just gone for filtration of this and removing the water. So there is a stacked nature of the graphene sheets is formed. So we found that the importance of the freeze drying method to form the 3D structure of the graphene and supported nickel iron layer double hydroxide. Further to know the this is for the 3D structure formation characterization. But further TEM image also suggested that the nickel iron layer double hydroxide particles are distributed, and the uniformly distributed, and the particle size are very small. Further high magnified image also you can see here, the particles are homogeneously distributed, and inside here you can see the selected area electron diffraction. Here the bright spot are formed, and which are systematically distributed, so because of their crystalline structure of the nickel iron layer double hydroxide. So as we have studied thoroughly for the without support and without nitrogen, as we already told that the in presence of nitrogen there is a contribution, because nanoparticles are growing in presence of the nitrogen, which changing the electronic environment of the graphene substrate, only carbon substrate. When nitrogen doped over that, then electronic distribution is completely changing. So here you can see without any substrate, that nickel iron layer double hydroxide, see the particle size how smaller it is. But in absence of any substrate like the 3D carbon we used, the particles are self-assembling and from the big particle size is formed. So, but here also another important factor is that without using any nitrogen to venting nitrogen over the graphene, so here you can see that this is the things in presence of nitrogen. But in absence of any nitrogen, the particles distribution, that layer double hydroxide distribution is not homogeneous. It's in one place it's assembled and form a agglomerate structure of the nickel iron layer double hydroxide. So that thing further will confirm that the from the BET surface area measurement, that importance of the freeze drying. As BET surface area, from that we can measure the surface area of the materials, so from the nitrogen adsorption. So here you can see the without using freeze drying and in absence presence of freeze drying, so how BET surface area is changes. First, the red one is the without freeze drying method applying, so there is no such change in the porosity distribution is observed. Pore diameter it changes that. So but in the presence of the freeze drying systems, so here you can see the pores are intense peak is observed around 4 nanometers. So that is because of the presence of the microporosity in the material in applying the freeze drying method. To know the crystal phases formed in the nickel iron layer double hydroxide over the 3D graphene like nitrogen doped entangled graphene, here we check the nitrogen doped entangled graphene. The graphitic peak is so 002 peak because of the graphitic peak for which is coming around 26 degree. But in presence of the nickel hydroxide over the nitrogen doped entangled graphene, the similar peak is observed from 002 plane for the graphitic, and one another extra peak is coming from the nickel hydroxide, and which we confirm through the JCPDS value, that formation of the nickel hydroxide. But after incorporating iron into the nickel hydroxide, which is from the nickel iron layer double hydroxide, the peaks are 002 peaks for the nitrogen doped entangled graphene, the graphitic peak, and another peaks are coming, so which we compare to the JCPDS number, so which shows the formation of the nickel iron layer double hydroxide. But that as the Raman analysis we have done to know the, as we are using the graphitic carbon like graphene oxide as a substrate. So first graphene oxide having, we have checked the Raman id by ig value, that id is the defect and the g is the graphitic. So id by ig value means defect into the graphene nature is the around 0.95. It is almost similar defect and id by ig value. But when you are applying the freeze drying method and we form the nitrogen of entangled graphene, so their id by ig value is coming around 1.25. So there you can see the changes from here, that 0.95 to 1.25 there is a changes is observed. So that because of the higher ratio of higher amount of defect creation in the nitrogen of entangled graphene, that already is shown in the FECM image, their defect presence is high amount in case of the nitrogen of entangled graphene. But after incorporating the nickel iron layer double hydroxide over the nitrogen of entangled graphene, there is not that much change is observed. Here you can see, so that is because the nickel iron layer double hydroxide is not changing the graphitic structure any distortion. But so this higher id by ig value compared to the graphene may causes the not that much changing id by ig value, but the still defect is increasing, so that may be helpful for the electrochemical performance. So because in electrochemical performance, graphite id by ig value should be optimum value that could helps to the better activity as well as the durability. Because if the graphitic nature is very less, then there is a chance of more corrosion, as I already shown in introduction slide. The graphitic structure is needed for better durability. Second thing, as we already told, that the importance of the nitrogen and the metal particle anchoring. And the second thing is that we have checked the TGA. This is the thermal gravimetric analysis to find out the catalyst, because active center is the nickel iron layer double hydroxide, and this is the support. So here you can see the without any support nitrogen double entangled graphene, when we are heat treating in presence of oxygen, there is residual metal presence after the 400 is 0%, because it is but in case of nickel iron layer double hydroxide without any carbon substrate, when you are heat treating, there is a changes in the weight, so which because of the water molecule presence in the intercalation structure. Already shown the nickel iron layer double hydroxide, there is a intercalation structure. So in between two layers there is a water molecule which maybe connected through hydrogen bond, and so that removed after a 200 degrees centigrade, that change is observed. So that's why 16% weight loss because of the intercalation water molecule. But another two thing is that nickel iron layer double hydroxide entangled graphene framework, and another is the nitrogen dope entangled graphene framework. So these two are suggesting that what is the importance of the nitrogen for metal nanoparticle loading over the carbon substrate. So these here you can see, in absence of any nitrogen doped over the carbon, metal loading is less compared to the in presence of the nitrogen. So this changes the 20% to 35.3%, that in presence of the nitrogen, they are already in 10 images shown that the uniform distribution and more numbers of metal layer double hydroxide can anchor over the nitrogen dope entangled graphene. But in absence of nitrogen, there is a less, and the see the team image also, there is a agglomeration of the particle and the less numbers of particle supported over the graphene. So from that we confirm that the nickel iron importance of the nitrogen dope over the 3D graphene and the nickel iron layer double hydroxide, how they are distributed. So morphology we confirm, but their chemical environment and the presence of the iron nickel we confirm through the X-ray photoelectron spectroscopic analysis. So this is the survey spectra for nitrogen dope entangled graphene framework. So here presence of the three peaks, intense peak for carbon one is, and another in two peaks is for nitrogen and oxygen. But after incorporating nickel iron layer double hydroxide over the nitrogen dope entangled graphene, the another peak appears here. So this is because two peaks, one for the iron 2p, another one is the nickel 2p. So first, as introduction slide, I told that the nitrogen could doped over the graphene substrate in various form like pyridinic, pyrrolic, or oxidized on another form. So here also we the deconvoluted spectra suggested that there are four different kinds of nitrogens are present. So here importantly, as we are using the graphitic nitrogen, heat treating 180 degree, so doping the graphitic nitrogen is there is no possibility of the graphitic nitrogen formation. So which is a very important thing, because graphitic nitrogen only participating for electronic conductivity as well as the durability. So in low temperature, when you are heat treating, there is a no chances formation of the graphitic nitrogen. So that is very much beneficial for the better stability. But other things, whatever the forming the pyridinic nitrogen and the pyrrolic nitrogen, which is helpful for the electrochemical activity, and the more percentage of present here the oxygen nitrogen, secondly the pyrrolic nitrogen, which is very responsible for the any kinds of electrochemical performance. And that nitrogen can help to hydroxyl ion adsorption during the electrochemical performance. Further deconvoluted spectra in case of the nickel 2p, here we can see the two peak and two satellite peak is formed. So that suggested that the presence of the nickel in by comparing the binding energy plus 2 oxidation state of the nickel, and another one is the iron 2p, which is formed two deconvoluted spectra. So presence of the iron plus 2 in plus 3 in oxidation state by comparing this. So from these we can confirm that nickel iron layer double hydroxide having the plus 2 and iron plus 3 oxidation state, and the morphology from that we can confirm the from this kind of physical characterization we confirm the nickel iron layer double hydroxide formation and their uniform distribution and the importance of nitrogen. So further we check the electrochemical performance by using the RD, that ring this electrode. So rotating this electrode. So here we have done in 1 molar KOH all the experiment, 1 molar KOH. So first we check the electrochemical surface area, that is double layer capacitance measurement. So as when electrochemical surface area is double layer is directly proportional to the electrochemical surface area of the material. So importantly here you can see the nickel iron layer double hydroxide hydroxide. This is the only without any support, the double layer capacitance value is very less, like 1.1 millifarad per centimeter square. But in presence of the support, like nitrogen doped graphene, that is without freeze drying system, already shown in the FESM image that the graphene sheet are stacked. So that there, although their value is high presence of carbon, but the value is a huge difference when you are going to nickel iron layer double hydroxide in presence of the nitrogen to ventral graphene support. So this huge difference in the double layer capacitance suggesting that our catalyst, the layer double that freeze drying having a great importance for the better double layer capacitance, because this is directly correlating to the how many ions can adsorb over in the surface. So further, this is the LSB plot. We checked the electrochemical oxygen evolution reaction and compare with other catalyst we prepare. So this is the nickel nitrogen only carbon substrate. There is very less onset potential, the over potential. Higher over potential. But when you are going for the nickel iron layer double hydroxide, so there is the on OER activity is higher, but better value we are getting for the nickel iron layer double hydroxide nitrogen to ventral graphene. So this peak 1.4 around it is coming for the nickel oxyhydroxide formation. So from that we are getting the better value for our predicted catalyst nickel iron layer double hydroxide supported nitrogen to ventral graphene. To know the kinetics, we have done the TEFL analysis, TEFL slope to measure the kinetics of any particular reaction. So here you can see the nickel iron layer double hydroxide supported nitrogen to ventral graphene shows the lower value of TEFL slope, like 68 millivolt per decade, which is having a better kinetics compared to the other catalyst. So any electrocatalyst, not only activity, durability is a very good characteristics parameter to know the how long it can perform, because activity is a primary factor. Second thing, how long it can show. So as here you can see the over potential is coming around 1.2 volt, because this is a comparable value to the solar to fuel formation. So here 1.52 is the onset potential. So from by where oxygen evolution reaction started. So there 1.52 volt we kept it for a long time, that how long it can shows the oxygen evolution. So here you can see it is around almost 20 hours is showing the oxygen evolution reactions. But here you can see the noise is coming because oxygen evolution is the oxygen bubbles form in the rotating this electrode. Then after a certain, when bubble size is very less, we are applying the rotation, so it removed, then suddenly current is improving. Then that up to a certain times there is a surface morphology changing, so that's a surface roughness changing, that's why there is no noise is coming. So similarly we have done the cyclic voltammetry study also from 1000 cycles in keeping the same potential window. So there we are getting also after 1000 cycles there is no such change in the initial, and after 10,000 cycle the LSB plot. So which suggested that our catalyst having the best activity as well as the durability. To further know the importance of the nitrogen doped over the graphene, we have compared the LSB plot without nitrogen and in presence of nitrogen. So there is a huge change in the activity. Similarly, we have done the impedance measurement. So here you can see the impedance for our catalyst is showing the lower charge transfer, so higher charge transfer resistance, so that it's for better activity. So we have compared the various catalyst reported previously, like similar catalyst to our catalyst. So here we are getting the 68 TEFL float, which is comparable to the previously reported, and the onset potential that is over potential we are getting here 290 millivolt, which is less compared to the similar kinds of catalyst. So in conclusion, I can say that in presence of the ammonium hydroxide, formation of the layer double hydroxide and the nitrogen doped could be a very much good factor to improving the performance. And secondly, our catalyst is showing the lesser over potential, which is and onset potential is around 1.52 volt, and we show a good stability, which is around 20 hours with 80% retention of the current density. So thank you all for your kind attention.
My name is Soshu Kirihara. I come from the Osaka University, Japan. And today I would like to talk about directional fabrication of the ceramic components by using ultraviolet laser lithography of additive manufacturing process. So at first, I would like to talk about the stereolithography and the conventional type and the three-dimensional fabrication process. Okay, in our investigation groups, we try to fabricate the various kinds of three-dimensional structures. For example, the periodic structures and the self-similar fractal structures by using ceramics or other metals and composite materials. Okay, so the plate-shaped structures and three-dimensional structures were fabricated by using stereolithographies. So this figure shows the principle of the photonic crystals. Today, I would like to talk about the periodic structure fabrications of the photonic crystals. Okay, so here is the dielectric materials. So the periodic structures possible to reflect the electromagnetic wave whose wavelength is similar to the periodicity like this by Bragg diffractions. So in this case, the photonic band gap and prohibited and band gap areas created in the frequency range in the transmissions attenuations. In this case, and the standing wave A and the standing wave B form in the crystal structures, and the standing wave A vibrating in the air region with higher frequency, and the standing wave B vibrating in a material region with a lower frequency. And between higher frequency and the lower frequency, all electromagnetic waves will be reflected by Bragg diffractions. So that in this area, the photonic band gap areas, electromagnetic wave impossible to transmit to the opposite side, and this means a perfect reflections of the electromagnetic wave. Okay, if you create cavity-shaped photonic crystals, you can transmit the electromagnetic wave for one directions, and you can create like the plate-shaped crystals, and it realizes the barrier functions of the electromagnetic wave. Of course, the parabolic shape and the photonic crystals realize the direction transmissions of the microwave, millimeter wave, or the more higher frequency electromagnetic wave. Okay, what is the ideal structures of the photonic crystals? The one type is like this, the diamond type, because here the diamond type photonic crystals possible to open the photonic band gap for all crystal direction like this. So this blue band shows the common regions for the all directions photonic band gap. So in this frequency areas, electromagnetic wave impossible to transmit to the any directions or the artificial crystal directions. However, and of course, this photonic crystal is a perfect structures. However, and it is difficult to fabricate like this complicated lattice structures by using a conventional fabrication method. So in our investigation group, we try to fabricate the photonic crystals by using a stereolithography like this. Okay, here this figure shows schematic illustrations of the photonic crystal fabrications. Here is a photosensitive resin. This resin solidifies the UV laser irradiation. So the laser scanning, and we can create like this the line shape and solid materials. And these line structures was created, many lines were created on the like this stage plate. And okay, layer by layer stacking process, we can create the three-dimensional structures. So we can create the plastic three-dimensional structures by using only the laser scanning and the layer by layer stacking. Okay, this figure shows the created and the photonic crystals. In this case, the epoxy mold and inverse the lattice structure, inverse diamond structures was created by stereolithography. And titanium barium titanate and the paste materials insert into their three-dimensional mold, so we can create a photonic crystal like this. However, it's difficult to inject to the material paste to the three-dimensional mold, so we try to mix the ceramic particles into the photosensitive liquid resins. Okay, and in this case, two-dimensional structures by using a laser scanning, and through the layer by layer stacking, we can create a three-dimensional pattern like this. Okay, so we can create by only the laser scanning and the layer by layer stacking, and we can create a complicated shape three-dimensional structures by using a stereolithography process. Okay, this figure shows fabricated diamond photonic crystals, In this case, the titanium dioxide particle was dispersed into the epoxy matrix, and the volume fractions just only the 10%. So the the direct constant is not so high. However, these three-dimensional structures and the periodic structure directions is about 10 millimeters. So the possible to reflect the microwave by using these three-dimensional patterns. Okay, and the microwave property was measured by using like this the metal tubes. Okay, and here is antennas, and here is antennas, and the microwave transmits the samples, and and the transmission attenuation measured like this. Okay, if the fabricated photonic crystals possible to reflect the electromagnetic wave in the limited frequency range, attenuation will be decreased like this. The U-shape profile will be obtained. Okay, and this figure shows a fabricated titanium dioxide particle dispersed epoxy diamond photonic crystals. You can see the 111 and the 100, 110 crystal plane obtained according to their computer graphic data. Okay, so the microwave transmits to the 111, 100, and 110 directions. Okay, this figure shows a transmission attenuation of the microwave. You can see and all crystal directions, and from 12 gigahertz to the 70 gigahertz, and the band gap form of all crystal directions. For example, the 15 gigahertz microwave impossible to transmit for any directions. This means the perfect reflections. Okay. So the next, and the electromagnetic property of the photonic crystals possible to calculate by using the solving Maxwell equations. In this case, a plane wave propagate into the photonic crystals for all crystal directions. The most important thing, most difficult thing is how to enter the three-dimensional structure to the Maxwell equations. However, in this case, a computer graphic data were cut for the 32, 32, 32, and the XYZ data, and the Dielectric data were entered into the Maxwell equation automatically. So, okay, this figure shows the obtained electromagnetic band structures. This yellow line shows the Maxwell equations answer. Okay, here there are many Maxwell equation answer, and then of course this lower frequency and also. So there in these areas the Maxwell equation have answers. So the electromagnetic wave possible to transmit to the opposite side. However, you can see that these regions there are no yellow lines, so the electromagnetic wave is impossible to transmit to their opposite side. So this means perfect photonic band gap formation reasons. So these solid circle shows a higher edge and the lower edge of the measured photonic band gap. You can see the calculated result and the measurement result has good agreement. Okay. Anyway, we want to try to control the higher frequency electromagnetic wave, especially called the terahertz wave, the micrometer order wavelength electromagnetic wave. Okay, this far infrared ray regions and possible to detect like this small weapon behind the newspapers, and it possible to detect dangerous rock and by using a transmission viewing system. Anyway, we have to control, we have to fabricate a micrometer order diamond type photonic crystals to control the micrometer order wavelengths and the higher frequency terahertz wave. Okay, this figure shows a fabricated and micrometer order photonic crystals by using a conventional stereolithography process. And you can see the micrometer order lattice obtained. However, in this case, we used only the 0.1 millimeter, 100 micrometer spot size laser beam. So it is difficult to create like this micrometer order structures. And the most important thing, these are composite materials. The epoxy matrix absorbs the terahertz wave, so we have to create some more clear micrometer order diamond type three-dimensional structures, and by using a perfect 100% ceramics lattice. Okay, the next process is a nanoparticle pasting process. Okay, we tried to increase the ceramics particle dispersion amount in the photosensitive resins. And in this case, the 40 volume% alumina particles, and in this case, the particle diameter is 170 nanometer were dispersed into the acrylic, photosensitive acrylic resins, okay, by using a rotation and a revolution mixing machine. In this case, rotation means mixing like this, and the revolution means like this, the mixing. The revolution is the degassing, and the rotation is the mixing of the particles and the solid particles in the liquid phase. Okay, this is a movie that you can see there. Okay, at first the paste material is very hard, higher viscosity. However, if you introduce the stick and turn around the paste, and okay, you can see the paste material shows smoothly fluid flows. Anyway, we can control the viscosity by introductions of the shear stress. So this high viscosity paste was spread on the glass substrate by using a mechanical knife edge, and in this case, a layer thickness and 30 microns. Okay, so the laser beam scanned on the paste surface, so we can create a solid 2-dimensional structures. And spread and the laser scanning and the laser layer by layer stacking process, we can create 3-dimensional structures in unsolidified paste materials. After the fabrications, the 3-dimensional structures are put out and washing and drying, and we can obtain the composite materials. Okay, so this movie is stereolithography fabrication. Okay, paste materials and spread on the glass substrate. Okay, and this white color is laser scanning. Okay, so the paste materials are spread on the they are over. Okay. Okay, this figure shows a fabricated micrometer order photonic crystals. In this case, the alumina particle are dispersed into the acrylic resin matrix, and the volume fraction is 40%. Okay, okay, you can see the micrometer order. The diamond lattice was obtained by using a laser scanning stereolithography process. So, of course, these are the composite materials. We have to create a full ceramics micrometer order lattice. Okay, by using a conventional dewaxing and sintering process, we can create the full ceramics 3-dimensional structures. Okay, and after higher temperature sintering process, we can create a full ceramic diamond lattice. Okay? You can see the diamond planes in 111, the 100, 110. Okay, and you can see the micrometer order alumina lattice and the translucent lattices. And reached the relative density. In this case, the 99.8% very higher density. Okay, so we can create the full ceramic diamond structures by using a stereolithography and heat treatment process. And the terahertz wave property was measured by using like this optical system. At first, a femtosecond laser beam inserted into the micrometer order antennas and generated the terahertz wave transmit sample and detected the same shape micro antennas, and we can obtain the intensity and the time and the pulse data, so that by using Fourier transformations, and we can obtain the transmission spectrum. Okay, this figure shows obtained transmission attenuations, transmission spectrums. Okay, and you can see there 110, 100, 110 directions, and we can obtain the photonic band gap in the similar frequency range. This blue band shows the common regions of the all crystal directions, For example, the 0.4 terahertz wave impossible to transmit to any directions. This means the perfect photonic band gap formation. Okay, the photonic crystals, why we call these structures the photonic crystals, okay? Here is a schematic illustrations of the semiconductors. These materials compose of the periodic structures of atoms. These periodic structures possible to reflect the electronic wave by Bragg diffractions. So in this case, the electron band gap form in the energy band. And if you introduce the donor or the acceptors, the structural defect to the semiconductor, you can create a localized mode in the electronic band gap, and you can control the electronic wave transmissions by introduction of the structural defects. And of course, in the photonic crystals, imitation of the semiconductors and this periodic structure, dielectric material periodic structures possible to reflect the electromagnetic wave by Bragg diffractions. And the photonic band gap open in the electromagnetic wave transmission spectrums. And if you introduce a structural defect, you can control the electromagnetic wave transmission and create a localized mode in the band gap. Okay, so similar logic, the photonic crystals and the semiconductor natural crystals. Okay, this figure shows introduce a point defect in the perfect photonic band gap. Okay, so of course this hole was fabricated under stereolithographic additive manufacturing process. Okay, this figure shows a calculated result. In this case, the incident wave and the localize and resonate here, and all here is the perfect reflection structures, and making a standing wave increase the powers and transmit to the opposite side. In this case, half wavelength localize here, and in this case, one wavelength localize this directions. And these electromagnetic wave only transmit for opposite side. Okay, this figure shows the the measurement result. The photonic band gap opens by your perfect photonic crystal structures, and introduced the structure defect creates a transmission mode of the transmission peak of the localized modes, okay, in the specific frequencies. Okay. This figure shows the created ceramic crowns. Okay, we can create various kind of three-dimensional structures in the photonic crystals. Of course, the photonic crystals and the bioceramic structures, and we can create various kind of materials and three-dimensional structures. However, we have to create the three-dimensional shape by stereolithography, and if you obtain the full ceramic structures, we have to use the heat treatment process. Anyway, we need two processes, shaping and heat treatment. So the next trial, direct ceramics fabrication by using a laser scanning process. Okay, in this case, laser beam, ultraviolet laser beam powers increase to the 1 watt. This is 10 times higher comparing with the conventional stereolithography process. Okay, so increase the power ultraviolet laser beam, realize the waxing and through the resin decompositions and sintering by using electromagnetic wave resonation, localizations, and absorption. Here is the ceramic space materials. After the waxing and sintering process, remaining ceramic particle was sintered and creates the plate-shaped structures on the substrate. Okay, this figure shows a laser drawing process and the bright color obtained the laser spot side. And after laser scanning, we can create like this plate-shaped materials. Okay, here is microstructures. You can see the micrometer or the bulks created in their microstructures about 5 micron to the 8 microns. And of course, at first, the ceramic particle size is under the 1 micrometers, so the micrometer or the bulks were created by laser beam irradiation. The most important is spread paste thickness at first 15 micrometers. However, after laser drawing, the layer thickness decreased to the 25 micron. This means the ceramic particles dispersion is 50%, so the waxing and sintering shrinkage occurred to their only z directions. So it is possible to realize the layer by layer stacking process. Anyway, in our investigations, and we used ultraviolet laser beam and 355 nanometer wavelengths. Okay, in this case, a half wavelength easy to propagate between the particles and the penetrate into the inside of the paste materials and increase the temperatures, so the resonation and the localization occurred over the inside, so that the resin dewaxing and the powder sintering were realized the inside of the paste materials. However, if you use the infrared ray and wavelengths in the very longer, and the laser beam impossible to penetrate into the paste materials, so they're okay by laser beam scattering. Anyway, layer by layer stacking process, we can create micrometer order 3D structures. In this case, a titan and photonic crystals was created by ultraviolet laser scanning process. And at first, here is a micrometer order structures. However, in this case, the nanoparticle were coagulated into the 3D structures. So the scanning speed increased to the two times, and the scanning speed 100 micrometer per second, so we can obtain the more clear micrometer order structures. However, you can see the black area remained. Of course, this is the remained carbon elements, so the irradiation power was increased to the 600 milliwatt to the 700 milliwatt, so we can obtain the white colors micrometer order titanium dioxide lattice was obtained. In this case, the relative density is 97%. Okay, high density, however, not so. We want to try to do the heat treatment. So, in this case, after heat treatment and the lattice crystal structures was luteal structures or higher dielectric constant. Okay, and by using directional fabrications and ultraviolet laser lithography process, we can create twin diamond structures. Okay, here is real structures, and this dotted lines are twin defect. Okay, here right side and the left side has a mirror symmetric diamond lattice. Here is a plane defect. This area is possible to localize and resonate electromagnetic wave. In this case, the sintering density reached 99.5%. Okay, this is localized simulations, and the wavelengths and the electromagnetic wave localize and resonate here, and reflects my perfect mirror structures and increase the powers and to transmit to the opposite side. Okay, this figure shows the calculated results and measurement results. Here is a band gap, and here is a localized mode formed by introductions of the plane defect of in the twin diamond crystals. Very clear photonic band gap and localized mode was obtained in the measurement results and the calculated results. Okay, in this investigation, we try to fabricate the 3D structures by using additive manufacturing process. At first, the 3D diamond structure was designed, and the 3D pattern was fabricated by a stereolithographic additive manufacturing. And the electromagnetic wave property was measured by a computer system and obtained the result feedback to the 3D designing. By using like this investigation circles, we can create the ideal structures, and by using computer-aided design, manufacturing, and evaluation process. Anyway, this is last slide. In our investigation groups, we can fabricate various kinds of 3D structures. Of course, the ceramic structures and the metal structures and the composite materials. And today, I talk about the periodic structure fabrications and the electromagnetic wave controls by using photonic results. Thank you very much.
Well, good evening. I don't know how I want to remove. Well, good evening. Thank you for coming, for listening this conference. My name is Esperanza Cortez. I'm a PhD of the Chemical Engineering Department from the University of Huelva. And the piece of work that I want to show you or to share with you today deals with the development of novel thickening formulation by using natural deep eutectic solvents as a matrix base. Well, here are the guidelines of point that we are going to see. In the first time, we will do an introduction into lubricant area. Secondly, we will see the instrument and methods used in the experimental process. Next, I will talk to you about the results obtained from several tests. And finally, I will conclude with the most relevant results of this study. Well, the lubricant industry wants to minimize the impact on the environment by replacing petroleum-based raw material by renewable resources. In previous research, the use of vegetable oil as lubricant base has been studied. In addition, biomacromolecules like natural waxes, resin, and polysaccharides with gelling properties in oily media have been reported. Therefore, the main objectives of this study of this work will be the development of renewable formulation with suitable properties. Well, in this sense, although vegetable oils like castor oil was proven to be an excellent candidate to replace mineral oils in lubricant formulation, they saw some limitation regarding some physical and tribological properties and chemical stability, requiring chemical modification or the incorporation of some additives prior to their final use. For that, we bet by the use of one moment. I don't know how well now. We bet by the use of natural deep eutectic solvent formulation, which are mortal salts or liquid at room temperature, forming a three-dimensional supramolecular structure, and so several advantages and outstanding properties, physicochemical properties. Moreover, their low cost, biodegradable character, and sustainability reinforce their potential use as raw material for application in different fields. On the other hand, agro-industrial resource from biomass with a large worldwide production and biodegradable characteristics seem to be good option to be used as thickeners. Well, following this direction, this work explores the possibility of using NADES formulation, which involve an hydrogen bond donor compound and an hydrogen bond acceptor compounds comprising hydroxyl groups in its chemical structure as lubricant base, and lignocellulosic materials previously modified by epoxidation, favoring the chemical cross-linking in order to produce green thickened liquid or gels. Well, now we are going to see the synthesis protocol to use to develop these biolubricants. It is divided in 3 steps. Firstly, the synthesis of NADES was carried out by mixing all the components at 56 Celsius degree for 1 hour. In this case, 3 hydrogen bond donor compounds were selected in this work. I mean glycerol, xylitol, and sucrose, containing a different number of hydroxyl groups forming its molecular structure and using citric acid as hydrogen bond acceptor. Moreover, as can be seen in the table, different amounts of these reagents and water were required to obtain stable liquids at room temperature, which allows also to modify the viscosity properties of this blend, I mean the addition of water. Therefore, we are going to analyze the influence of the hydroxyl group number in the final properties of our thickened formulation. Okay. Well, in the second step, lignocellulosic material was chemically modified through epoxidation, carrying out the reaction with neopentyl glycol diglycyl ether and mixing lignin deposit compound and water in an open vessel at room temperature during 3 hours. Finally, the product was centrifugated, washed, and dried just to obtain the epoxidized material. And in the last step, This modified lignin and this NADE formulation were mixed in an open vessel, adding a 30% of the thickener agents and reacting during 3 hours at room temperature. Finally, the blend, the thickened formulation, was homogenized with a rotator turbine. Well, once formulations were synthesized, they were characterized through infrared spectroscopy tests, thermogravimetric analysis, and finally, both NADES and thickened, the final gels, were characterized from a rheological point of view by using 2 different rheometers and apply flow and frequency sweep tests inside the linear viscoelastic region. Well, now we're going to start with the result and discussion. As previously discussed, the synthesis of NADES was successfully carried out by mixing all the components according to the proportion that we can see on the table, achieving homogeneous mixtures at the eutectic point and stable at room temperature. In general, NADES structure is influenced by the different interaction occurring between carboxylic groups of citric acid and hydroxyl groups of hydroxyl group contained in the hydrogen bond donor compounds. And for that, different proportions of these compounds are required to attain this eutectic point, as you can see here in the table. Moreover, for this formulation, as previously detailed, the addition of water is required to obtain this stable mixture forming a supramolecular structure, needing a greater amount of water as the number of hydroxyl groups forming the hydrogen bond donor compound was raised. I mean, in the sucrose, we need a higher amount. In the sucrose-based sample, we need a higher amount of water than the other one. This is due to the stronger interaction arising in its microstructural network as a consequence of the high number of hydroxyl groups. Moreover, water allows to modulate some properties of this formulation like viscosity or polarity, which also will condition the final properties of the thickened samples. Therefore, a supramolecular structure is obtained in all cases, comprising physicochemical properties that will depend on both water amount and the number of hydroxyl groups forming the hydrogen bond donor components, and will condition the rheological properties of the final formulation after dispersion of epoxidized lignins. Well, in this segment, now we are going to see the infrared spectroscopy test, which allow to verify the chemical interaction occurring between both materials. I mean, NADES formulation of modified lignin and also the formation of a microstructural network. Well, as can be seen in the figure, in this place, the chemical modification of lignin can be verified by means of the disappearance of hydroxyl bands. In the black line, we can see the vibration of hydroxyl group, which has disappeared in the red line. Also detecting the appearance of a new peaks related with the CO bonds resulting from the epoxy ring opening. This allows to verify, therefore, the chemical reaction occurring between open epoxy rings and hydroxyl groups of lignocellulosic materials. Besides, the availability of free epoxy ring in the lignin chemical structure for further reaction can be corroborated by the appearance of these two peaks, which are related with the epoxy ring vibration. So we can verify in this way the availability of this group just to react with NADES in the thickened formulation. On the other hand, we can verify this cross-linking reaction between the epoxy groups contained in the lignocellulosic materials and the hydroxyl groups contained in NADES formulation by the disappearance of these three peaks that we can see here in the green line. these bands are not appearing, are not present, are not shown in this spectrum. So the chemical cross-linking, the reaction or the chemical cross-linking reaction has been done successfully. Well, this is the same. In the same way, we can verify this chemical reaction by means of thermogravimetric analysis, which allow to verify the chemical modification of lignin, as well as the interaction with NADES in NADES formulation. And for lignin, there is just one peak at around 360 Celsius degree, which is related with the cleavage of multiple linkage forming the lignin skeleton, together with an overlap thermal event at around 260 Celsius degree, typical of the soft dehydration of hydroxyl groups. The chemical modification of lignin gave rise to a decrease in its thermal stability due to the introduction of the epoxy compound in its structure. And as we can see, two new peaks, two new degradation events were found in this curve for epoxidized lignin, which can be related, the first one with the existence of free epoxy ring available for further reaction, and its isomerization by means of CO bonds excision when producing the epoxy ring opening. On the other hand, the chemical interaction between NADES and modified lignin could be verified also by the disappearance of these two new peaks in the modified lignin, two new thermal events related to the epoxy, the existence of free epoxy ring, which prove the reaction with the hydroxyl groups contained in NADES mixture, leading to the formation of a new secondary hydroxyl groups as a consequence of the epoxy ring opening when the reaction between both groups is carried out. Well, now we are going to see the rheological behavior of these compounds. As we can see that NADES, in this table, we can see that NADES can exceed so high viscosity values that limit their use in many applications. Being able to modify these properties, as I detailed earlier, by varying the amount of water. In general, as can be seen on the table, Newtonian characteristics with important differences in viscosity were obtained when modifying the hydrogen bond donor compound. I mean, obtaining very high viscosity values for sucrose-based sample than the other ones. In this way, sucrose, which contain the higher number of hydroxyl groups, reveal the highest viscosity value due to the sucrose chemical structure, whilst the other ones show very low viscosity values. Thus, the more hydroxyl groups that are available to react with carboxylic group of citric acid, the more hydrogen bonds are formed, leading to an increase in viscosity. On the other hand, in the figure show the viscous flow curves of lignin structure NADES as a function of hydrogen bond component, hydrogen bond donor component and flow. In this case, the three NADES evaluated yield highly structured shear thinning liquid, which much higher viscosity than those provided by NADES as a result of the chemical cross-linking. In this way, a power law model was used to describe shear thinning characteristic of this formulation, where K and M are the consistency and flow indexes respectively. As expected, the higher consistency index was obtained for the formulation prepared with sucrose, which also exhibit a slight more enhanced shear thinning character. I mean, these values was higher. On the other hand, just in order to elucidate the effect of NADE's viscosity on the viscous flow properties of thickness formulation, we have I plot here the relative viscosity versus shear rate, obtaining a similar behavior, a similar viscous curves for the three kinds of NADE used. This indicates that lignin exerts a very similar structuration role in the three NADEs, and the difference in viscosity are mainly due to the NADE's viscosity. So we achieve the same structuration degree in all samples when dispersing lignin. Well, finally, the formulations were evaluated from a viscoelastic point of view, obtaining different rheological behavior depending on the type of hydrogen bond donor compounds used in the synthesis process. The values of both the storage and the loss moduli increase when with the number of hydroxyl groups comprising the hydrogen bond donor component, showing both viscoelastic moduli similar values and characteristics of soft gels, which resemble either a viscoelastic response close to critical gels or a glass transition from a cross-linked network. In this way, formulation containing glycerol and xylitol as hydrogen bond donor compounds in the eutectic mixture show higher values of the storage modulus, the G prime, than the second one at low frequencies that tend to achieve a plateau region here. However, a crossover between both source functions was identified at intermediate frequencies, which is close to critical gels materials. However, for sucrose-based samples, despite the higher values of both modulus, G2 was always higher than G prime in the whole experimental frequencies range study, which is the typical behavior or the typical viscoelastic response for material achieving a glass transition. Well, attending to the previous discuss, I can conclude that NADE's formulation with a supramolecular structure were successfully achieved in this work, displaying properties that are influenced by the water amount forming the blend and the number of hydroxyl groups comprising the hydrogen bond donor components. Infrared spectroscopy and thermogravimetric analysis tests confirm the chemical cross-linking occurring between hydroxyl groups of NADEs and epoxy groups contained in the modified lignin. NADE's formulation show a Newtonian characteristic exhibiting a sucrose-based sample the higher viscosity due to the higher number of hydrogen bonds forming their network. Lignin-based product display shear thinning characteristics as a result of the chemical interaction between the epoxy groups of lignin and the hydroxyl groups of the eutectic mixtures. Lignin exerts a very similar structuration role in the three NADEs, being the differences in viscosity due to the NADE's viscosity. And finally, viscoelastic behavior of lignin-based formulation can be modulated by modifying the hydrogen bond donor compound comprising the eutectic mixture, obtaining from soft gels to glass materials. And that's all. Thank you for listening to me. And if you have any question, it's a pleasure for me to answer you.
Okay. Thank you for the nice introduction. And my name is Adrián Tenorio. Well, I have two surnames, so sorry for the... Okay, so Adrián Tenorio, and the study I will show you today is the result of a collaborative investigation between the Chemical Process and Product Technology Research Center from the University of Huelva, to which I belong, and the Department of Chemistry from the University of Florence. This study is entitled Thermal and Structural Analysis of polycaprolactone fluoronic blend films obtained from thermomechanical processes. I'd like to start with a brief introduction and, well, biodegradable polymers has emerged as invaluable materials with a wide range of applications within the medical field, including drug delivery, tissue engineering, regenerative medicine, and temporary implantable devices, among so many other applications. However, when we want to consider a material as biodegradable, it has to meet some basic criteria, not only the biocompatibility and lack of toxicity, obviously, but also good mechanical properties, good, an appropriate degradation rate, along with, I will use the, sorry, just give me a second. I'm looking for the pointer. Yeah. A good durability and obviously a low cost. Well, considering all of that, and among all the likely biologically metabolizable materials, like for example, polylactic acid, polyglycolic acid, polycaprolactone, polyhydroxybutyrate, and so many other polymers, PCl excels owing to its outstanding properties, including the good biocompatibility, what is expected, of course, and also the non-toxicity, but not only before, but also after its hydrolysis. Then it also has is manufactured, reduced prices, and a good permeability to a wide range of chemicals, what is quite important when considering drug delivery applications. On the other hand, biodegradability of polycaprolactone strongly depends on not only the degradation conditions, but also on its intrinsic properties, including crystallinity, molecular weight, morphology, and so on. Bearing that in mind, the modification of the polymer network properties may allow us to somehow customize the ultimate performance of the resulting polymer, the biodegradable polymer. To this respect, bulk blending of PCl with other materials has appeared as a feasible choice due to its process simplicity and the lack or the absence of additional reagents during this process. Indeed, the incorporation or blending of PCl with Cryonics has demonstrated the suitable modification, well, not the modification, better said, the enhancement in the stability and biocompatibility of PCl when considering drug delivery applications. Probably some of you are not so accustomed to the use of Cryonics. For those of you who don't know them, Cryonics are triple copolymers comprising hydrophobic polypropylene oxide and hydrophilic polyethylene oxide. And that mixture is what provides them their amphiphilic properties, and also the ability to tune or to modify those ultimate properties of the resulting polymer blend, I mean. Well, with that in mind, the aims of this study were first, modification of PCl with Cryonic. In this case, we chose, there are so many kind of Cryonics, but we took Cryonic F68 and at two different concentrations, at 5 and 8.5 percentages, and using hot melt extrusion followed by pelletization, and then the obtained pellets were compressed molding, obtaining the final polymer blend. And then the other aim was the evaluation of the structural organization and crystallization of those biodegradable polymer blends. To do all of that, we applied the following experimental techniques. First of all, we analyzed their thermal properties by means of differential scanning calorimetry. We applied this analysis under nitrogen atmosphere and conducting heating and cooling cycles within the temperature range from -80 up to 120 degrees Celsius. Then the structural organization of the obtained polymer blends was studied by both a small angle X-ray scattering and also X-ray diffraction, and both of them conducted at room conditions. Well, moving on to the result section, I think, we can start with the DX results, and this graph shows the results of the pure compounds in the lower part, and also the data corresponding to the polymer blends in the upper part, and both of them containing the heating and cooling cycles. As we can see in the lower graph, from the lower graph, although melting temperature of both pure compounds were quite close to each other, that thermal event was much more intense in the case of pluronic, in comparison obviously with the PCl, even doubling the energy consumption during that thermal process. As a consequence of that, the incorporation of pluronic into neat PCl promoted the crystallization process, and that was noticeable not only in the higher crystallinity degree corresponding to the black line in the graph on the right, but also in the higher, not also noticeable in the higher crystallization temperature corresponding to the red line. On the other hand, these polymer blends exhibited a second crystallization step at around -10°C, and although that peak didn't appear in the pure compounds, its energy release rose with the addition of pluronic, highlighting not only its reliance on the presence of pluronic, but also on its content. Well, in order to delve into the impact of adding pluronic into neat PCl, we apply a deconvolution of the melting peak, and we suitably deconvoluted that peak into 3 individual Gaussian peaks, confirming what we found in literature, that not only the crystalline phase, but also some partially ordered mesophases can be found, containing condyles and plastic crystals or crystal morphologies. Indeed, we couldn't identify to which of these peaks those crystal morphologies corresponded, but we observed that although all these 3 peaks appear in all cases, not only in the polymer blends, but also in pure PCl, the addition of pluronic modified the individual contribution. Well, we analyzed the individual contribution from the areas contained in these peaks, and we observed that upon addition of pluronic, the peak located at 56°C was promoted. But apart from that, we couldn't identify to which of them correspond each crystal morphology. Bearing in mind that pluronic, maybe I didn't say that, but sorry for that, but pluronic are water soluble, and taking that into consideration, these polymer blends were submitted to a 1-year immersion in distilled water, and then subjected to the DSC tests. Upon water immersion, the release of pluronic was corroborated by the reduction in their weights, obviously more importantly in the case of the system with the highest pluronic content. That was obviously expected. But apart from that, we observed that upon immersion, all these systems exhibited at a much lower crystallinity degree. Moreover, we also applied the previously indicated the convolution of the melting peak in the upon immersion in water, and we compare those results. I mean, the individual contribution of the Gaussian peaks with those values corresponding to the before the immersion in water. And as we can see, the peak corresponding to the red color, that one at 60°C, dramatically decreased, even disappearing in the case of the system with the lowest pluronic content. And that, together with the lower crystallinity degree values obtained upon immersion corroborated the nucleating effect of pluronic into PCl. Okay. On the other hand, the morphological parameters, including the long period and also the crystalline and amorphous layer thicknesses associated with the lamellar structure, and obviously the lamellar structure is typical of PCl, could be extracted from the such results. Indeed, we apply a 1D correlation according to some previous investigations to obtain those parameters. As we can see in that graph, although no significant influence can be found on the amorphous layer, the incorporation of pluronic into PCl dramatically reduces the thickness of the crystalline layer, as we can see in that reduction. From those results, we could also analyze the crystallinity, but well, better say the linear crystallinity according to this equation. But this crystallinity only considers those crystals with the lamellar structure or the lamellar arrangement. If we compare those values obtained from SACS, that blue line, with those obtained from the BSc tests, we can see that in the case of pure PCl, there is a good agreement between the two techniques. We have almost the same crystallinity degree, indicating or denoting that PCl has, or all the crystal in PCl has the same lamellar conformation. However, when adding pluronic, a great reduction in the linear crystallinity can be seen in comparison with the DSC results, which takes into account the overall crystallinity of the system. And that may note that there must be some other crystal or some crystal that have other kind of conformation different from the lamellar structure. Well, in order to obtain not only a qualitative but also a quantitative somehow description of those crystal morphologies, we also apply X-ray diffraction at the microscale. And as we can see from the Xrd pattern, all the system, not only the planes, but also the pure PCl, the red line, the black line, exhibited the orthorhombic structure, as can be seen from the characteristic peaks corresponding to the orthorhombic unit cell. Apart from that, we also confirm the partially amorphous character of these materials from the peak located at around, I think that was around 12 degrees. Well, from these patterns, we evaluated also the crystallinity degree. And as we can see from the green line, that would be the corresponding to the Xrd test, there is, or generally there is a good agreement with the DSC test, indicating that all the crystal present in this polymer, in the blends or in the pure compound, have the same orthorhombic conformation. Well, indeed, only the system with the lowest pluronic content deviates from that trend, but it is worth to mention that this system has a large heterogeneity that may lead to a inconstant behavior when conducting this kind of test. We have so many different values resulting from this test, but we just took one of them. Now, if we evaluate by a similar deconvolution as we did in the DSC results, if we analyze the individual contribution of the lamellar and the mesophases, we could differentiate the condyles and plastic crystal. We had to to evaluate them together, we can see that upon addition of pluronic, the mesophase content increase, even almost doubling, and indicating that the addition of pluronic resulted in a higher or increased conformational disorder in PCl, hindering the chain folding that may lead to the lamellar crystals. Therefore, although obviously some discrepancies can be found between the different techniques that can be expected, of course, but despite the overall increase in the crystallinity degree, the higher mesophase content upon addition of pluronic may explain the lost crystallinity obtained from sacs. Okay, finally, and just not to extend too much, because we are almost at the end of the webinar. So we also apply XRD test over the system after water immersion. And we corroborated again the same orthorhombic structure in all these cases. But more importantly, after water immersion, we confirm the lower crystallinity degree as we saw in the DS results. But not only that, also we obtain a higher mesophase content as a consequence of the release of the pluronic into water. Well, just to summarize the main conclusions, in this study, we modify PCl with pluronic F68 by using extrusion and pelletization, followed by compression molding processes. Then addition of pluronic F68 promoted the crystallization of polycaprolactone. The predominant lamellar arrangement of PCl was corroborated along with the presence of partially ordered mesophases, including condyles and plastic crystals. Moreover, addition of pluronic into PCl rose the mesophase content in detriment of the lamellar arrangement. And finally, after 1 year of immersion in water, we found the release of pluronic into water by both the weight loss of the samples and the reduction in the crystallinity degree, also improving the content of mesophases after that immersion process. That's the end of my presentation, and thank you very much for your attention. I think I can stop sharing. Right.